Okay, so, well, welcome back everyone. Welcome to the second day of the summer school. It's my pleasure to introduce Andrea Martins, one of the co-founders of the school and a colleague here at IST. So, Andrea did his PhD in the dual degree CMU Portugal program with advisors here and at CMU. His work on machine learning for NLP tasks like syntactic parsing received the prestigious IBM Research Award. Currently, Andrea is an associate professor here at Technical. He is a senior researcher at IT. He is a VP of AI research at Sambado. And he has work spanning many different areas in NLP. So he's currently also coordinating the Deep Spin ERC project here at Technic. Is co-guiding the ELIS NLP program together with Irina Gorovic and Ivan Titov. And yeah, he has an amazing set of PhD students. Some of them you'll meet also here at the school as monitors. Okay? So the talk here today is about machine learning with linear models. I'm sure you'll enjoy the talk very much. And well, let's all welcome Andrea. Welcome to speak.
Okay, thank you very much. Oops. Okay, can you hear me well? Good. All right, thanks for the introduction, Grim. Yes, so today we are going to talk about linear classifiers. The first question that you might be asking is why do you need to have this lecture? Today everyone uses neural networks for everything. Why should we care about linear classifiers? So I'm trying to convince you that it's still useful to have this lecture for a few reasons. One is that this is a gentle way of presenting some machine learning concepts that are the same, either if you're talking about linear classifiers or neural networks. It's a lot easier to understand parts of the theory in statistical theory and optimization theory when you are using linear models than deep learning models. Linear classifiers are still widely used for in industry in some tasks. They are usually very effective if you don't have enough data for more sophisticated models to work better. And linear classifiers can also be seen as a component of neural networks. So to be a little bit more precise, this is a neural network. The lecture on neural networks is going to be tomorrow. So if you don't understand this feature, don't worry so much about that. But here we have as inputs an image, and the goal is to classify this as a dog or a cat. So there's a bunch of neurons connected to each other. This is a fit for the neural network. But if you focus on the last layer, the output layer, then this part can be seen as a linear classifier. Okay, so there are some representations here. We can also call them features. And this output layer is basically you can see it as a linear classifier. So what we are going to talk about today has to do with which loss function makes sense to use for this output layer and different properties of these things. All right. So the big difference is that in linear classifiers, typically you don't learn internal representations as you do with neural networks. Rather, you handcraft features. So you need someone who knows something about the domain of the problem and is good at designing good features to capture the properties of the image that have to do with dogs and cats. Okay, so this is the roadmap for today. I'm going to start by talking about linear regression. Then I'm going to cover binary and multi-class classification. We are going to cover some well-known linear classifiers, such as the Perceptron, the naive Bayes algorithm, logistic regression, SVMs. I'm going to talk a little bit about softmax and sparse-max. And then we are going to talk about regularization, a little bit about optimization, about the stochastic gradient descent algorithm. And if time permits, I will briefly talk about similarity-based classifiers and kernels. And by the way, feel free to interrupt me with questions anytime. Okay, so let's start by giving some example tasks that we're going to bring again over and over in this lecture. The first example is a binary classification task. that you see every day when you're reading your email. You might have seen that there are spam filters that are able to detect if an email is spam. Sometimes it's not very accurate, sometimes it is, and this saves you a lot of work. This is an instance of a binary classification task. Given the text of an email message, should I classify this as spam or not spam? Okay, so there's only two labels here. Another example is another example of a multi-class classification problem. If we're given as inputs a news article, for example, this news about AlphaGo, this was a huge success in 2016. So we are given this text as input, and the goal is to classify what is the topic of this article. Is it about sports? Is it about politics? Is it about technology? And so on. So usually you have a closed list of labels. And the goal is to output the label that best describes the topic of this document. Okay, so I'm going to start by talking a little bit about data and feature representation. And some of the slides that I'm presenting now, they are adapted from a lecture by Ryan McDonald, who gave this lecture at the summer school several years ago. And let me start with a very simple task, just a toy task to motivate what I'm going to present afterwards. So let's suppose that we have a very small training set, just with 4 examples. Each example is a sequence, okay? And each sequence has exactly 3 symbols. So the first sequence has these symbols, star, diamonds, and circle. The second sequence is star, heart, and triangle, and so on and so forth. And for each of these sequences, we are given a label, okay? So, and there's only 2 possible labels, -1 or +1. So this is an instance of a binary classification problem. And now we have been trained with these 4 sequences, and then at test time, there is a new sequence showing up, and our goal is to predict what should be the label. And this is it. We don't have any further information about the problem. So if you see this sequence, what would you predict? Which label would you predict here? -1 or +1? -1. Okay, that was quick. And why -1?
It's the same as example.
Exactly. So this is really easy, right? So the model can just memorize the sequences, and it might realize, oh, I already saw this sequence, so I'm going to predict exactly the same label that I've seen. And this seems to be like a safe choice. Okay, if there is some stochasticity, maybe this is not the correct label, but if you need to choose between one or the other, it looks a lot safer to pick -1. Okay, so what about this one? -1, and why is that? Okay, so that's a good strategy. So this is a little bit harder because it's not exactly the same as any sequence that we have seen, but you can look at some patterns of this sequence and match these patterns with our training data. So for example, if you look at stars, we see stars in 3 examples. 2 of them have the label -1, 1 of them has a label +1. Okay, then diamonds, they're also present in both, but arts, they only exist in a single example whose label is -1. So there seems to be, I don't know, it seems that -1 matches better this example than +1. So we will predict -1 here. And what about this case? +1 for the same reason. Okay, so let's who thinks who would vote for -1 here? No? I see a few arms. What? Okay. Okay, so yeah, so this is a lot more difficult. Okay, so there are arguments that go in one direction or the other. Okay, but let's first think about how can we do this. Okay, so what are we doing that allows us to make these predictions? So one very intuitive strategy is just to look at these patterns. Each pattern is a single symbol, and you can count how often you see each symbol together with a given label. So for example, this is for the second sequence that I showed you. If you have stars, diamonds, hearts, then we can see that stars occur twice with the label -1 in these 2 examples, and they occur once with a label +1. So we can estimate the conditional probability of the label being -1 given that we observe stars. and this will give us 2/3. On the other hand, the probability of +1 given stars will be 1/3. Okay. Then we can do the same thing with the other symbols. Okay, so with diamonds, we see half of the time. So there is one example which is -1, another one which is +1. So the probability is going to be 50% for either. And hearts, it only occurs once, and it occurs with a label -1. So it's going to have 100% probability for -1 and 0% probability for label +1. So there seems to be more evidence towards the label -1, and I guess this might be the reason why you picked -1 when you saw this example. So this is the sequence that Carol was saying that it could go either way. And in fact, if you count the patterns, that's exactly what's happening, right? So again, stars occur 2/3 of the time with label -1 and 1/3 with label, with label -1 and 1/3 with label +1. But if you look at triangles, it's the opposite, okay? So they occur once with label -1, twice with label +1. So the probabilities are flipped, and circles, they occur once for each of the labels. Okay, so there is no good reason to pick one versus the other. Of course, we are doing some assumptions here. Okay, and it's good to come back to this example and see the assumptions. For example, with this reasoning, I'm not modeling the order of the symbols. Okay, I'm just saying that I'm just counting how often I see a symbol together with a label. You know, maybe if we understand what this language means, maybe the order is going to be important, but with so few examples, there's probably no good reason to make very strong assumptions about that. Okay, so this is kind of a toy description about what we often need to do in machine learning. So one thing that we need to do is to define a model or a distribution of interests to model our problem. We need to make assumptions. We always need assumptions. So this if needed is almost always an even. And then we need to fit the model to the data. Okay. And as we do that, then we are able to use that same model to make predictions on unseen data. So in this simple example, our model is a probabilistic model. We are modeling the probability of a label given a sequence, and the sequence is just a sequence of symbols. And if you want to make a prediction for a new sequence, then we are going to pick the label among these two possibilities that maximize the conditional probability of label given sequence. It seems very reasonable. And now, which assumption are we making here? The assumption that I just mentioned, that the order of the symbols doesn't matter and so on, and the reasoning that we do when we count it, how often each symbol occurs with each label, this corresponds to something called the naive Bayes assumption, which is something that I will come back in this lecture. And this assumption is basically saying that all the symbols are conditionally independent given the label. Okay, so in other words, the probability of the sequence given the label, which is the same thing as writing the probability of the joint probability of all symbols conditions on a label, can be written as a product of probabilities where each probability is regarding a single symbol given the label. This is called the naive Bayes assumption. And then, as we are clear about which model and which assumptions we are making, the next step is just to fit the model to the data, which means estimating these probabilities. Okay, and for that, what we did was basically just counting and normalizing. Okay, so of course, if you have more sophisticated models, things are not as easy to do as with the naive Bayes model. We're going to cover a few in this lecture. But so let me start by defining some notation that we are going to use throughout the lecture. So I'm going to denote inputs by X. So the lowercase letter X denotes an example. And this calligraphic set X is our input space. This is our set of possible examples. And in some of the examples that I'm going to show in this lecture, assume that X might be something like a news article or a sentence or an image. And then we have our outputs, which I'm going to denote by lowercase y. And this calligraphic set y is the output space, okay? The set of all possible outputs. And there's many different outputs depending on which problem we are trying to solve. But in the examples that we saw in the previous slides, the output space y could be just a set of two labels, spam or not spam. Or it could be a set of topics, in which case the lowercase y will be a particular topic. It could be something more sophisticated, like a parse tree for a sentence. or a segmentation for an image. And then often we also need to talk about input-output pairs. Okay, so this means X and Y together. An input together with its label. For example, a news article together with a topic, a sentence together with a parse tree, or an image which is partitioned into segmentation regions. Okay. Okay, so now, and the big focus of this lecture is, and actually many of the lectures that will follow, is supervised learning. Okay, so what this means is that we assume that during training, we have access to a labeled training set. This is a set that contains input-output pairs. Okay, so someone told us that, oh, for that example, the label should be this one. Okay, so we can form this data set with pairs xn, yn. So we have n examples. For each example, we have the input and we have the corresponding label. This is what supervision means. Okay, someone is telling us what the labels are. But this only happens at training time. So what we want to do is to use this training set to learn a predictor. A predictor is just a function h, which goes from the input space x to the output space y. And we want this predictor to generalize well to arbitrary inputs, including inputs that we never saw before. So what we want to do at test time is, if you're given a new example x, a new input, you want to predict y by applying this function h. Okay, and we are going to denote our predictions by y hats. And hopefully we want y hats to be correct most of the time. Okay, so we want our prediction y hats to be close to y most of the time, and we are going to be more precise in a bit about what this closeness is going to mean. This also depends on which problem we are solving. Okay. Any questions so far? All good? All right. So I guess for many of you, you already saw this before. Okay, so depending on what our output space is, we call different names to these problems. So for example, in regression, we are dealing with continuous output variables. And if you remember Mario's class yesterday, he talked about continuous random variables and discrete random variables. This often implies that we are using continuous random variables. Okay, so for example, if you are predicting a continuous quantity like time, we often have to deal with a regression problem. So an example is when y is the set of real numbers, and the input is again a news article, but now instead of wanting to predict the topic of that article, we want to predict how much time some user is going to spend reading it. Okay, so we want to take as inputs the text of the article, and we want to predict a continuous quantity, which is time. This is an instance of univariate regression because there's a single variable that we are predicting. Another example is multivariate regression. Okay, so this occurs if you are predicting not just a single continuous quantity, but multiple continuous quantities. For example, and it's interesting if these quantities are correlated with each other. So one example of that is, for example, our output being an image, and you want to predict the position of the image where a user is going to click, given by its XY coordinates. So in this case, you need to predict two real numbers, the X and the Y, right? To define the position in the image. And it's also a regression problem, but now multivariate regression. There's a lot more, of course. Apart from regression, we also have classification. And here we are dealing with discrete output variables. The simplest case is a binary classification problem where there's only two labels. And throughout this lecture, when we have binary classification problems, I'm going by convention just to say that the labels are +1 and -1. This is just convenient, as we are going to see. But of course, this model fits problems where labels have particular meanings. For example, in spam detection, why is spam or not spam? We can just assign -1 to spam and +1 to non-spam, or the reverse. And from that point on, we have a binary classification problem. A generalization of that is multi-class classification, where we can have k labels, where k can be greater than 2. Topic classification is an example. We have k topics. We want to classify a news article into one of these topics. Another example, which is even more sophisticated, is structured classification, where the output space can be exponentially large and structured. An example of that are, for example, is for example machine translation, where the input is a sentence in one language, and you want to predict a sentence in another language. Okay, and of course there's infinitely many sequences that we can come up with. Other problems are if you have a sequence as input, and you want to label each element of that sequence in the output. And the number of labels the number of different ways of labeling an entire sequence is going to grow exponentially fast with the length of the sequence. So this is called structure prediction or structure classification if you are talking about classification. There's lots of problems that fit this framework. I'm not going to talk about this today, but later in LXMLS, in Noah Smith's class and Chris Dyer's class, they're going to cover this. So today we're going to stick mostly with binary and multi-class classification. Okay. So sometimes it's possible to move from some of these problems to another. This is called reducing a problem to a different form. For example, logistic regression reduces classification to regression. This is going to be covered in the second part of this class. And one versus all is a technique that allows us to reduce multi-class classification to binary classification. We're also going to briefly talk about that. Greedy search is a way to reducing structure classification to multi-class. We are going to see it later. But some other times it's better just to tackle each problem in its native form, okay, which is basically what we're going to do here. Okay, so let's move on to feature representations. And this is where linear classifiers distinguish from neural networks. In neural networks, usually we don't spend a lot of time engineering features. We just spend a lot of time designing a good architecture for a neural network, and then the neural network is learning good internal representations for us. Here, instead of using the neural network to learn internal representations, we have to manually we need to understand the domain of the problem, and we need to manually handcraft some of these features. This is also our opportunity to inject our knowledge about the problem when we are designing a classifier for that model. There's tons of examples for that. For example, in texts, bag of words features are very prevalent. How many of you know what bag of words features are? Okay, quite a few. Okay, so basically, for those of you who never heard this before, for example, if you have a document, a news article, like the example that I had before, we can represent that document by what are the words that occur in the document and what's their frequency, discarding the order of the words. So, for example, you can say that the words machine appears 3 times, learning occurs 4 times, and so on and so forth. And you just represent the document as a vector, where each index of the vector corresponds to a word, and the values are frequencies, relative frequencies or absolute frequencies. There are several variants of that. But bag of words means that we have, it's exactly that. It's like we have a bag of words. We don't care about the order of the words. We put everything in a bag, and we can have, it's like a multi-set, right? So we can have a word occurring more than once in the same document. And bag of words features are very common in texts. Okay, so given a document, we ignore the structure and the order, and we just count how often we see words in the text. There's more sophisticated things like looking at word lemmas. If we have words that inflect, for example, if you speak Portuguese or another language for which verbs usually inflect, if you are saying, if you are using a verb in the past tense to refer to third person and so on, the word is slightly different from the infinitive form of the word. And the lemma corresponds to the, so the lemma is a way to canonicalize this, to map all verb forms to a single form. Parts of speech tags is morphological information. Is this word a noun, a verb, an adjective, and so on? And these things are examples of features that are commonly used in natural language processing. In computer vision, there's other sets of features. They kind of fell out of fashion. Wavelet representations, sieved features. These days, people just use a convolutional neural network to take your pixels and map them to feature maps. But back in the day, they used to design filters manually to come up with good feature representations. in other problem domains, it's common to use a mix of categorical features, Boolean features, continuous features, and so on. So what this means is for categorical features, you have some set of attributes. For example, if we're talking about text, we could be referring to different morphological tags, let's say noun, verb, determiner, adjective, and so on. And if you are modeling a particular word, we have a category that is that corresponds to the morphological tag of that word. Okay, and there is exactly one of these tags that is the correct, the others are not. And one way to represent that is by having a vector with the size, where the size is the number of attributes, and then we use a one hot vector to represent that feature. I think I'm going to talk a little bit more in a bit about this. Boolean features are things like true, false. For example, does this sentence start by a capitalized word? Or does this sentence end in a question mark? So there are only two possible values, either yes or no. And it's possible to model that as a binary entry in a vector. Continuous features are things that involve real numbers. And we have that, for example, if you are projecting the data to a lower dimensional representation. For example, if you use things like PCA, or even if you have a neural network that preprocesses the data and turns that into a dense vector. So I'm going to be agnostic about which features we are going to use, but I'm just going to assume that there is going to be some map that I'm going to call phi. We call it a feature map that takes our inputs x and produces a vector which is d-dimensional. Okay, d is the dimensionality of the feature space. So we can see this map phi as a map that goes from our input space x. This is our original input space, and maps it to the Euclidean space, d-dimensional Euclidean space. Okay, so the phi of x is going to be a vector. It can be very high dimensional if d is very large. And we are going to use these vectors to encapsulate these different kinds of features. You know, they can all be mapped to the same vector. You can mix Boolean features with categorical features, with continuous features, and so on. Any questions about this? So who already knew this, by the way? Okay. So this used to be the bread and butter of machine learning 10 years ago. These days, I think it might be different because people are exposed to neural networks right in the beginning, and they don't talk so much about how to do feature engineering. But this is really important in linear models. Okay, so going back to this figure that I had in the beginning with the neural network and focusing on the output layer, then what we are doing is assuming that some expert is really good at defining features that depend on the image and that represent properties of the image that are useful to classify the image as a dog or a cat. Okay, so this is what I mean by handcrafted features. So, I'm going to talk a little bit more about NLP because this school is a bit biased towards natural language processing. So the classical approach to NLP before deep learning took over was basically stacking together multiple linear classifiers. This was forming like a big pipeline. So, for example, the first pipeline could be just taking text as inputs and segmenting text into sentences. Then the second step in the pipeline could be taking each sentence and classifying each word with its morphological tag. And then another step of the pipeline would take the words themselves plus the proto-speech tags and would compose them in some way to get features and would predict, for example, the syntactic tree corresponding to that sentence, and so on and so forth. Maybe you want to do some semantic task in the end. But this was like a pipeline, and we put different linear models on top of each other. This is the classic approach. Now, the tendency is very different. We learn things end to end. But so for a classical NLP pipeline, some features that are typically used are word occurrences. This is just modeling if a word occurs or not. It's a Boolean feature, a binary feature. Another example are word counts. This is a little bit more powerful than occurrences because it's really counting how often a word occurs. It's not just binary, but it's going to be a real valued feature. Sometimes you use relative frequencies, you normalize and do things like that, or do TF-IDF. This is something that you might have heard. Another example of features are part of speech tags. For example, if you are developing a system for sentiment analysis, adjectives are really important to predict sentiment, because they carry a lot of information that can have some positive or negative polarity. And it might be useful to identify where are the adjectives in this sentence, okay? And part of speech tagging is a way to get there. So it's common to use features that includes part of speech tags, morphological tags, for the words in the sentence. Another example are spell checkers. For example, we can check how many of the words match words that we see in the dictionary, how many spelling mistakes we see. This is a good feature for spam detection because many spam messages, to evade spam filters, they slightly introduce typos in the words. But if you have a system that looks at this, it can be more powerful to detect spam. Okay, so I'm going to talk about a problem that is a little bit less common, but it's very related to an actual challenging problem that I work on. It's called translation quality estimation. I guess several of you, all of you already played with Google Translate. And actually today in the evening, we're going to have a lecture by Slav Petrov. I think he might talk a little bit about translation, about Google Translate. But this is actually outdated. If you try it now, I think you might get the correct translation. But a year ago or something around that time, if you put this English sentence as input, the translation in French will be this, which if you don't know French, don't worry, but this is a wrong translation. So this is basically taking the words work in English as if it was a noun, and it translates it as travail. Okay, so it's the wrong translation. This translation is incorrect. And the problem of quality estimation is when you are given a source sentence and you are given an hypothesis for a translation, a candidate for a translation, we want to predict how good is this translation for this source. Okay, this is a useful step after machine translation. If you're translating sensitive content or content in a domain like medical domain, legal domain, and so on, where critical errors can have really bad consequences, it's useful to do quality estimation just to see if the system estimates that this is good to go or not. And so yeah, this is the goal of quality estimation: estimate the quality of translation on the fly without any reference. And well, this is very outdated. The best systems for quality estimation these days are based on neural networks. But back in the day, it's crazy the amount of handcrafted features that people came up with. And this is just like a quick snapshot. It's much more complex than this. And this includes things like things that are very intuitive. For example, counting how many words we have in the source, how many words we have in the targets. If there is a big discrepancy, maybe this might be a sign that maybe the quality is not good. Of course, languages can have, some languages are more succinct than others in the number of words. And sometimes you don't even have the concept of word like in Western languages, but this is a feature. Okay, so we are not saying that if we see a discrepancy, we are immediately going to flag this as low quality. This is just a feature, and the model is going to learn a weight for this feature, and this is going to be combined with a lot of other features. For example, a language model probability of a source and target segments. We are going to learn about language models in 2 days in Noah's lecture, so I'm not going into that. Counting different sizes, different n-grams. Well, there's all sorts of stuff. I'm not going to get into this. So it takes a lot of work to actually handcraft these features, trying them out, seeing if they are improving the system or not, and so on and so forth. In general, feature engineering is a black art. It can be very time-consuming, but it's a good way to encode prior knowledge. In particular, if you are working in a startup and we still didn't collect enough data, it might be the case that the neural network is not going to perform very well. So maybe you have a good intuitive understanding about the problem that you are working in, and it might be actually not that hard for you to design features and experiment with that. So this might be a good place to start. One alternative to feature engineering, of course, is representation learning. This is what is going to be the topic for the classes after this one. So Biksha is going to talk about this tomorrow. But today, just stick with feature engineering. Actually, I'm not going to talk more about feature engineering. Now I'm going to talk about what happens after someone designs features. And I'm going to start by talking about regression. Okay, so regression, as I mentioned in the beginning, assumes that the output space is continuous. We are predicting a continuous quantity. So let's use this example. We are given an article, and we want to predict how much time a user is going to spend reading it. You see this, for example, in Medium, when you have this. I don't know if you can read it, but in Medium you have. Before a post, you see an estimate about how much time it takes to read that post. I don't know how they do that there. I bet it's something really simple, nothing very sophisticated. Here I'm going to talk about very simple models. So let's assume that the content of the article doesn't matter. Of course, this is a very strong assumption. It should matter. But let's assume that the only thing that is relevant is the number of words of the article. Okay, so our X is just one number. It's the number of words. And you want to predict Y, which is the reading time in minutes. Okay, so we want to come up with a model that predicts Y hat from X. Okay, so if you had like 5 minutes to solve this problem, how would you do that? Anyone? Any suggestion? Yeah.
Count the average seconds per word.
Okay, yeah. So, let's assume that you collected some data. So you have some pairs X, Y, and now you want to come up with a model that predicts Y when you're given a new document. You can do something like what you are suggesting, but using your data to learn your model. So this is like a common first take. You assume that there is some dependency between X and Y, and we might assume that it's just linear to start with. We collected some data. The data is represented in these points. Okay, so the X-axis is the number of words. This is our inputs, and you want to predict the time in minutes. And you might, it's naive, but you might assume that it's just a linear relation. So we assume that Y is of the form Wx plus B, where W and B are model parameters, and we want to estimate these parameters from the data. Okay. So these points are our training data, the most common method to fit the model parameters in a model like this is the least squares method. Okay. So we are just going to given some W and B, we get a Y hat. And you can just penalize the sum of squares, or the mean of squares, between the true time, yn, and our predicted time, y hat. Okay, so this amounts to minimize this error function. Okay, how many of you already saw these squares before? Okay, I was expecting that. So this should not be big news. Do you think that these squares, the way I describe it here, is going to work well in this problem? Is it, or is it not? I see some. Okay, so yeah, if you look at this plot, it doesn't really look like a straight line. So least squares is going to try to fit a straight line because it's a linear model. It assumes that Y depends linearly on X. So it's going to, the plot is going to be a straight line, and these points don't really look like aligned in a straight line. So maybe it's not going to be great. It's not going to be bad. I think we can do something decent. But for example, if you get the X, which is very long, maybe we are going to overestimate the amount of time. Okay, so often if you just do this, it might be a poor assumption. So we can do a little bit better. So our second take is going to be developing some features, not just using a single feature, which is the number of words, but maybe we can use some polynomial features up to some degree. For example, we can define our feature vector phi of x, and we can assume that phi of x contains different monomials of x, including a constant feature of 1, x, x squared, and so on. Note that if you do that, we define this phi of x, and then we assume that our prediction is going to be the dot product between our weight vector w, this is the model parameters that we want to estimate, and the feature vector phi of x. Okay, so this dot product is going to return a scalar number, a real number, and this is going to be our prediction y hat, our estimates of the number of minutes people will spend reading this article. So note that because we are using a constant feature here, somewhere we are going to have W0 multiplied by 1, and this is going to be the bias parameter. So it's going to correspond to this B parameter here. Okay, so we don't need to explicitly model it if we include a constant feature. I'm going to come back to this a little bit later. This is just showing the basic example. Okay, so now what we need to do is to fit the model parameters W. Now it's a vector instead of just 2 parameters. It can be more than 2. We're going to have a weight for each feature, and we want to minimize again the sum of squares. So it's basically the same thing as before, but now we have more features. How can you do that? If you already learned least squares, you might have seen that okay, we are minimizing a loss function. We can just compute, well, this loss function is convex. This is something that I'm going to come back with later. You can just compute the gradient of this loss function, equate it to 0, solve the equation, and this is going to give us a closed form solution. Okay, this is something very particular of linear regression that you don't have for other predictors, as we are going to see. So in the linear regression, with the least squares methods, you do have a closed form solution for fitting our model parameters to the data. Okay, and this is our closed form solution. We need to form a matrix capital X, where the rows of this matrix contain the features for each of the training examples. And we need to form a vector Y that contains all the targets values, all the reading times for all the examples in the training data. And then by doing some metric multiplication, inversion, and so on, we obtain the closed form solution for the model parameters. Okay, so this part here, X transpose X minus 1, X transpose, this is often called the pseudo inverse of X. I'm not going to get into details here. And we are kind of solving the system to obtain the best fit for our model. Okay. Note that even though we might have features here that are, so this is not a linear in X anymore, but it's still linear in W. Okay. So we still call this linear regression, even though you might have a higher order polynomial fitting the data. We're not going to have a straight line anymore in our original plot, but it's still linear regression because it's still linear with respect to the model parameters W. Okay. So this was the example that I had before. If we just use d equals 1, so if you have d equals 1, you just have 2 features, 1 and x, and the model just reverts to the one that we had in the previous slide. With d equal to 2, we get a parabola fitting these points, and it seems to fit them much better. So maybe this will be a much better choice. Okay, so again, it takes some knowledge of the problem domain. In this case, it's very easy. You just need to look at the points. But if it was a more complex problem, it could be more complicated. It takes some knowledge to be able to define the right features that are going to lead to a good classifier. Okay, so so basically, this is just restating what I had before. Linear regression with the least squares method, the method that we just saw, corresponds to using a particular loss function. This is the function that we are minimizing to fit our model to the data, which is called the squared loss. Okay, so we can see it as a loss function that takes the ground truth output y and the prediction y hat, and it penalizes according to this expression. Okay, this 1/2 is not very important. It's just a constant. If you minimize these without the 1/2, you're going to get exactly the same model as the solution. The 1/2 is going to be convenient to compute gradients and so on. So you often use it. Okay. And in this case, we are assuming that our model prediction is given by this expression, which is a linear with respect to the model parameters. Okay, any question about this? We are going to see this a lot in this lecture, this expression w dot product with phi of x, okay? Not just for regression, but for classification as well. This is what defines a linear model. Okay, so one thing. So yesterday you learned a lot about probabilities. There was this refresher on probability theory. It's interesting to point out that the least squares method, it's not just something ad hoc that we come up with. You know, there's actually a probabilistic interpretation that we can give to it. If you assume that the data is generated stochastically, like this, if you assume that there are some true model parameters, so you know there is some W star that we want to estimate, and the data is generated by you know taking phi of x, the feature representation of x, doing the dot product with the true model parameters W star, and then adding some noise. If you assume that the noise is Gaussian with zero mean and some variance sigma squared, which is fixed, then because we are adding here you know a constant, well, we are adding a deterministic quantity plus some stochastic noise, y will become also a Gaussian random variable with mean equal to this deterministic part, W star W asterisk dot product with phi of x, and variance sigma squared. Okay, so we now have a Gaussian random variable. Then it turns out that the model parameters that we estimate with the least squares method, using the method shown in the previous slide, corresponds to the maximum likelihood estimate under this model. Okay, it's actually very easy to show it in just one slide. I don't have lots of proofs in this lecture, but this is one of the few. You know, this is the definition of a Gaussian or a normal distribution that we saw yesterday, with mean mu and variance sigma squared. In maximum likelihood estimates, we are looking for the model parameters W that maximize the probability of the data given the model. Okay, if you assume that the data is generated IID, then this can be written as the product of the probabilities of each y given x and the model parameters W. Now, if you want to maximize a product of probabilities, we can also maximize the log of that, because the log is a monotonic function. Okay, we are going to get the same solution. If you take the log of a product, this is the same thing as the sum of the logs. So we obtain the sum of log probability of yn given xn W. And now, because we know that this is a Gaussian distribution, you know, by our assumption that the data is generated stochastically like this, then the log of this Gaussian, we can see that this is the log of something times an exponential. The log of a product is the sum of the logs. So I get the log of this part. Okay, I'm going to move it here. And we have the log of x of something. Log and x are going to cancel each other. And we get, as a result, the part inside the x, okay, which is this. Okay, so we obtain this expression. And I'm assuming here that the variance is fixed. We don't care about the value of the variance, but we just assume that it's constant. So this means that this term is constant. So it doesn't matter, we can get rid of it. And therefore, the model parameters that maximize the likelihoods, again, because sigma is constant, we can get rid of it. It's just a scale factor here. This is the same thing as minimizing the sum of squares. Okay, so the least squares method is going to give us the maximum likelihood estimate for this model. So a short way of putting it is that linear regression with a squared loss is the same thing as maximum likelihood estimate under Gaussian noise. Okay, any questions? Okay, so I talked about squared loss, but there's also other loss functions that can be used for regression. Some of them are widely used. One of them is the absolute error loss. In this case, instead of penalizing the sum of squares, you penalize the sum of the absolute value of the differences. So if you want to depict that as a plot, you know, here we have the error, which is basically the difference between y and y hats. The squared loss is just a parabola because it's this quadratic function here. This is the thing in red. The absolute loss is the thing in blue. Okay, so it's the absolute value of this difference. And there is also a loss function that mixes the two. Okay, I like it a lot. It's called the Huber loss. it equals the squared loss in the interval from -1 to 1, and then it reverts to something closer to the absolute error loss. And it's used, particularly used in robust statistics. If you have a problem with many outliers, outliers are points that are, wrong measurements, for example. The squared loss is very sensitive to these outliers, because if you look at the shape of the loss function, when the error increases, when y minus y hat is either very negative or very positive, then the loss function increases quickly, right? Because it's a quadratic function. The absolute loss doesn't penalize outliers that much, but on the other hand, it's non-differentiable in 0. And the Uber loss is kind of the best of both worlds. It's still differentiable everywhere, and it doesn't penalize outliers very much. So it's possible you cannot have a closed form expression for these two, absolute error loss and Uber loss, but it's possible to solve it with optimization, and it's widely used. Okay. Okay, so let's switch gears a little bit on and talk about something which is also important to mention, which is underfitting and overfitting. In the example that I showed you before with the simplest model to predict the reading time, you saw that our model was not really fitting our points very well. So we were underfitting. It's kind of like this plot here. Okay, it doesn't really look like a straight line is a great fit to this data. And eventually we came up with a balanced solution where the fit is better. But if we take this too seriously, then we can start overfitting our data. Okay, we can have a very complex curve, a very complex shape, which is fitting our points very precisely. Our training loss is going to get very small because the residuals of these points compared to the curve that we are estimating is going to be very small. But we are probably going to have very bad generalization because our model is overfitting our training data too much. If you show new test examples, the model might be really bad for them. So you want to avoid overfitting as well. And usually there is a sweet spot somewhere in the middle. We don't want to make our model too complex, but you also don't want it to make it too simple. Otherwise, it's going to underfit the data. And a way to control these problems is by adding regularization, okay, by penalizing the complexity of the model. So I'm going to talk a little bit more about regularization later, but since we are talking about regression, I'm going to mention a very simple regularizer for linear regression. And if you like the probabilistic point of view, one way of thinking about this regularization is as having a prior distribution for our model. We assume that our model W, the model parameters, without seeing any data, we have a very simple prior for it, which is our model being a zero mean Gaussian, okay, where all model parameters are independent of each other. So they're all independent with some variance sigma W. They have the same variance, and they have zero mean. So this is our prior distribution, and now we observe data. And we need to combine our prior with the probability of the data given the model. Okay, so this technique is called maximum posteriority. It's a very basic form of being Bayesian. We are not being completely Bayesian because we are still estimating model parameters, but we use a prior distribution where you can inject some knowledge even without seeing any data. And then instead of maximizing the probability of the data given the model, we maximize the probability of the model given the data. Okay, if you use Bayes rule here, the probability of model given the data is the same thing as the probability of data given the model times the probability of the model, which is a prior, divided by the probability of the data. The probability of the data does not involve the model. So if you are maximizing that with respect to the model, we can get rid of that denominator. And the objective becomes just the product of the prior with the conditional probability of the data given the model. Okay, so I'm going to come back to these things a little bit later on. But the point is that we are adding this prior to our objective. So before we didn't have that, we are just maximizing the product of the probability for each example. Here, we are adding this term here, which corresponds to our prior. So again, if you do the same thing, if we take the log of this objective, then we have the log of the product. This is the sum of the logs. So we have this extra term here, log of the prior, plus the thing that we had before. And now if you keep developing this, because you assume that our prior is a Gaussian distribution, then the log of this is going to take this form, because we have zero mean, plus some constant, which is going to depend on this variance. I'm assuming that this variance is constant, so I'm not going to worry about that. And at the end of the day, we get an expression which is just like the sum of squares plus some an extra term, which is the Euclidean norm of the model parameters. Okay, this is called the L2 norm regularization. And again, I'm going to come back to this. It's the most common form of regularization. But if you want to see it from a probabilistic point of view, you can assume that this assumes that you have a Gaussian prior for our model, and we are doing maximum a posteriori instead of maximum likelihood. Okay, any questions? Okay. Am I going too slow or not? Just there's a chance that many of you already saw these concepts. No? Okay, so I'm going to keep at the same pace. Okay, so this finishes regression. How am I with time? So I think we have half an hour and then the break. So I'm going to try to cover the perceptron algorithm and naive Bayes before the break. And then in the second part, we'll talk about logistic regression, SVMs, and the rest. Okay, so we saw regression. Now we're going to shift gears to classification, okay? And before going to multi-class classification, we're going to look at binary classification, which is a little bit simpler. So in binary classification, we assume that there's only two possible labels, and we are going to convention that the labels are -1 and +1. So, for example, if you are given a news article, is it true or fake? Or if you're given an email, is it spam or not spam? So again, we are going to do the same thing. We take our input and we are going to represent it with a feature vector, phi of x, and then we want to predict y hat from x. And the question is, how can we define a model to do that? So the most typical thing to do if you have a binary classification problem is to use the Sine function to make our predictions. So this means that we do something very similar to what we did with regression. We take our feature vector phi of x, we take the dot product with the model parameters w, and we add some bias. But now we should not take this continuous quantity directly because y is not continuous. Now it's either +1 or -1. So one way to map this continuous quantity to a binary value is just to apply the Sine function. Okay. The Sine function is a function which is going to have the value +1 if the input is positive or 0, and -1 if it's negative. Okay, so it's a discontinuous function x0. You can think of the argument of the Sine function, this part here, as a score for the positives of the positive class. So if this quantity is very positive, then the model is very highly convinced that the correct label is +1. If it's very negative, then the model is convinced that it's really -1. If it's somewhere close to 0, the model might be a bit uncertain. Okay, so now this is the main difference with respect to regression. And we might also think about the decision boundary. Okay, I'm going to present that here. So if we represent our training data as points in a plane. So in this example, we assume that you have two features representing these two axes, and then each of the points is going to be depicted according to its features. And I'm going to represent a point as a plus or a minus, depending if the correct label for that point is +1 or -1. Okay, and this is the training data. So the problem of finding a good classifier, a linear classifier, can be seen as an hyperplane that separates these 2 points, the positives and the negatives, that tries to separate them as much as possible. And then the decision rule, which is this Sine function, is basically looking at which side our new example is. If we see a new point on this side, then it's going to be on the red side. So the classifier is going to classify it as positive, as +1. If it's on this side, it's going to be classified as -1. Okay. So the learning problem is the problem of estimating the hyperplane parameters. Where are you going to draw the hyperplane? And we want to do that from our training data. Okay, so there's a few concepts that I'm going to introduce here. They will be important in the sequel. Given a data set like this, we say that the data set is linearly separable if there is such an hyperplane. So, if the arrangement of the points is such that we can find some straight line, some hyperplane that separates all the positive instances from the negative instances. Of course, this is not always possible. Here in the right, this data set is not separable. Okay, so there is no possible hyperplane that separates the negatives from the positives because they overlap each other. Okay, if the pluses and minuses are all mingled together, completely mixed, this might be a sign that our features are not great because our features are not powerful enough for us to discriminate the positive from the negative examples. Okay, so what we're going to do next is to present an algorithm that if the data set is linearly separable, the algorithm is guaranteed to find a separating hyperplane. And before doing that, I'm just going to mention that often we present linear classifiers omitting the bias term B. Okay, so instead of saying that the argument of the sine function is the dot product of W and phi of x plus B, we just omit B. And the reason for that is that, so if you omit B, we are talking about hyperplanes that are always passing through the origin. And we can actually omit B without loss of generality because we can always add a constant feature to phi of x. Okay, so if one of the entries, let's say the first entry of phi of x is a constant feature with a value 1, then the corresponding weight, the weight that is going to correspond to that constant feature is going to play the same role as the bias term. And this just simplifies notation, okay? So in the sequel, we are going to just omit the bias term by doing this. Okay, is this clear? So this is quite important because we are going to use this throughout. Any questions about why we don't need to explicitly include the bias here? Right. Okay. Okay. So the algorithm that I was claiming that it can find a separating hyperplane is called the Perceptron. One of such algorithms is the Perceptron algorithm. It was invented in the 50s by Frank Rosenblatt. It was actually implemented in custom-built hardware. There was this big machine called the Mark I Perceptron. It was designed for image recognition. The weights of the model were actually something mechanical. They were encoded in potentiometers, and the weight updates of the model during learning were performed by electric motors. So this is a very scary picture of how this machine looked like. And when this algorithm was presented, it generated a lot of buzz in the news. Not very different from what we see now when we see, things about language models and machines getting conscious and so on. So this is an example of how the news were told in the New York Times. And if you look at some parts of it, you see things like Dr. Rosenblatt, a research psychologist at the Cornell Aeronautical Laboratory, said perceptions might be fired to the planets as mechanical space explorers. And later, perceptions will be able to recognize people and call out their names and instantly translate speech in one language to speech or writing in another language. Mr. Rosenblatt said, in principle, it will be possible to build brains that could reproduce themselves on an assembly line and which will be conscious of their existence. Okay, so very bold claims at the time. Maybe not so different from what you're seeing today. But yeah, I really like the perception algorithm because it's extremely simple, very intuitive, and it turns out that we can prove very powerful mathematical results, from such a simple device. So it's an instance of an online algorithm. This means that it processes one data point at each round. So it takes an example, xi, it applies the current model for this example, and it makes a prediction. It's going to predict either +1 or -1. And then there are two possibilities. Either the prediction is correct. If it is correct, it's not doing anything. It's this reasoning that if it worked, let's not touch it. Otherwise, if the prediction is incorrect, then there is going to be an update where the model is going to be corrected by doing something that involves the feature vector. Okay, and here I'm going to omit the bias term, which is licensed from what I said in the previous slide, assuming that there is some constant feature. So we don't need the bias. And this is the pseudocode of the algorithm. So it's really simple. It's just a few lines of code. We assume that we are given as inputs our labeled data set. We initialize the model parameters to all zeros. We keep track of the number of mistakes that we are doing along the way. This is going to be stored in this variable k. And then we are going to have this big loop where at each time we get some training example, let's say xi, yi. Then we're going to use the current model, which I'm denoting here by wk. And we are going to use this model, taking the dot product between that and the feature representation of the example xi, taking the sine function, and this is going to be the model prediction yi hat. And then if y hat is correct, we don't do anything. We just take another example and process it. Otherwise, we need to update the model. If there was a mistake, we need to update. And the update is very simple. We just redefine our the model parameters, wk plus 1, as wk plus yi plus, times phi of xi. So basically, what this means is if the model is incorrect, but the correct label is plus 1, we are going to sum phi of xi. And this is going to make it more likely that next time the model is going to predict the correct label. On the other hand, if the correct label is -1, this is going to subtract this feature vector. Okay, so again, it's going to make it more likely that we predict the correct label afterwards. And yeah, so every time we do a mistake, we just increment our counter, which is counting the number of mistakes. And we do this either until we reach a maximum number of epochs or until there is no more mistakes. Okay, so the model gets everything right. So if you have like an entire epoch without any corrections, this means that you already found the separating hyperplane, so we can stop. And the output is going to be the last model that we are finding. There are several variants of these, but this is the original perceptron algorithm. Okay. Any questions about the algorithm? How many of you already knew the perceptron algorithm, by the way? Okay, a lot. So I guess today's class is mostly like a refresher, like yesterday's. Okay, so, but you might not have seen this. I don't know if you did or not. So the perceptron has a very interesting mistake bound. For introducing it, I need to come up with a couple of definitions. We saw already what it means for the data to be linearly separable. It means that you can find a separating hyperplane that separates all the positives from all the negatives. But we can also introduce the notion of separation margin. Okay, so we say that the training data is separable with a margin gamma, where gamma is a positive quantity, strictly positive, if and only if there is a weight vector u with unit norm, such that when we take the dot product between u and phi of xi for any xi in our training data, and multiply it by either +1 or -1, depending on the correct label of that point, the result is always going to be greater than or equal to gamma. Okay, so what this means is that the argument of our sine function, because u dot product with phi xi is going to be the argument of the sine function, is going to be either positive enough or negative enough for us to get the right prediction. So this is showing us that the model assigns enough high score or enough negative score to that example and gets the right label. Okay, so the second definition is the radius of the data. Okay, so this is very simple. It's just the maximum norm of the feature vector for any training points. Okay, so we have these two quantities, gamma and r, and then we have this theorem that was proved by Novikov in the 60s, shortly after the perceptron algorithm has been proposed, which gives us a bound in the number of mistakes that the perceptron algorithm does. So it says that if the data is linearly separable with a margin gamma, then the perceptron algorithm is guaranteed to find the separating hyperplane with a number of mistakes that is at most r squared divided by gamma squared. This is a very powerful result, and it's very intuitive if you think about it. It tells us that if the data is separable but the margin is small, then we might need, this gamma here becomes small, and we might need to do a lot of mistakes until we find that separating hyperplane, because it might be tricky to find a separating hyperplane. If the margin is big, then it should be easy to find an hyperplane. And R is just a way to calibrate the dimension, the scaling of our feature space. So the bigger the radius of the data, the larger the number of mistakes. Okay, so it's the ratio between R and gamma that matters. Okay, so this result is so nice, and the proof is so simple that I don't resist to have the proof here. And again, I'm not. I think this is the last proof in this lecture. Actually, I think there is another one in the second part. But it's very easy to prove these bounds. Okay, and if you want to disconnect, you can disconnect for the next minutes. It's not a crucial proof for this lecture, but you might appreciate it. So recall that the update that the perceptron is doing after committing the case mistake is updating the model parameters. WK plus 1 becomes WK plus YI times phi of XI. This is basically this step here. And based on this update, we can come up with a lower bound for the norm of the weight vector after these updates. Okay. To do that, we write the dot product between U and WK plus 1. So U is this unit norm weight vector that is guaranteed to exist because we are assuming that the data is linearly separable with a margin of gamma. Okay, so there is some U that satisfies this. And we can just compute the dot product between U and WK plus 1 after performing the perceptron updates. And because WK plus 1 has this expression, this can be written like this, nothing special. And because we are assuming that the data is linearly separable with a margin of gamma, then we know that this part is greater than or equal to gamma. Okay, so we get that the dot product between U and WK plus 1 is greater than or equal than the dot product between U and WK before the update plus gamma. And if you iterate this inequality k times, one for each mistake that we are doing, you obtain that this dot product is greater than k times gamma, where k is the number of mistakes up to that point. And now we can use the Cauchy-Schwarz inequality, which I think Mario mentioned yesterday. Did he? Okay, he did. Good. So it's a very nice inequality that is used to prove a lot of things. And if you remember it, it states that the product of the norms is greater than or equal than the dot product between the vectors. Okay. So because U as a unit norm, okay, then the norm of WK plus 1 can be written as the norm of U, which is 1 times the norm of WK plus 1. And now we can apply Cauchy-Schwarz, and this is going to tell us that this is greater than or equal than the dot product between U and WK plus 1. And from this inequality, we know that this is greater than or equal to k times lambda, times gamma. Okay, this is just half of the proof. It's giving us a lower bound on the norm of WK plus 1. The second part of the proof is coming up with an upper bound on the norm. Okay, so it's the opposite. Okay, and to come up with this upper bound, we just write the squared norm of WK plus 1. We have this update, so this is going to be the norm of a sum of two vectors, and then you can just expand that square, and this is going to give us the norm of the first plus the norm of the second, and because yi is either plus 1 or minus 1, we just obtain the squared norm of the feature vector plus 2 times the dot product between these and these, okay, which is written here. And now because now there's a few things, okay, we know that this part needs to be less than or equal to 0 because we know that we have done a mistake here. This is why we have this update. Okay. Therefore, we know that our prediction, which is the sign of WK dot product with phi xi, does not match the sign of yi. Okay. So we know that this must be negative. And we also know, because we assume that the data is as a radius of r, This is the concept that I introduced here. Okay, we know that the norm of phi of xi is going to be less than or equal to r. Okay, so basically you get this. Okay, the squared norm of wk plus 1 is less than or equal than the squared norm of wk plus r squared. And again, if you iterate this k times, we get that this is upper bounded by k times r squared. Okay, so to come up, even if you didn't follow this part, the rest is straightforward. So we have a lower bound on the norm, and we have an upper bound on the norm. Therefore, the upper bound needs to be bigger than the lower bound, right? So k times lambda squared, because we are talking about the squared norm, needs to be less than or equal than k r squared, and from that we obtain that k needs to be upper bounded by r squared divided by gamma squared. Okay, so it's a one-slide proof of the perceptron bound. This is not going to matter for the rest of the class, but I just find it interesting. Okay, so of course the perceptron has limitations. Okay, this is a very powerful result, but remember that it only works because we assume that the data was linearly separable. So the decision boundary of the perceptron is always going to be linear. It's going to be an hyperplane classifier. This means that it can solve problems that are linearly separable. If you build problems by taking some logic operators, it means that it can solve, for example, the or and the and or the and problem. Okay, so here if we have if you have two features x1 and x2, both features are Boolean, and the correct label is the or of the two, then our data set is going to look like this. We are going to have, this is not triangles and circles, but it could be plus ones and pluses and negatives and minuses. So we will have all the triangles in one side, all the circles in the other side, and it will be very easy to come up with a separating hyperplane. It also happens if you have, for example, the ends of negated x1 and x2. We also can find a separating hyperplane or this version. But if you have something which is not linearly separable, and the most famous example is the infamous XOR problem, then this is not linearly separable. Okay, so in XOR, the XOR function says that the XOR of x1 and x2 is only +1 if they have opposite signs, right? Then we are going to end up with this plot. Okay, so where we have the triangles here and the circles here, and there is no way a linear classifier can separate the triangles from the circles. So it's impossible to solve this problem in this form with the perceptron. It's never going to find a separating hyperplane because there is no separating hyperplane. There is a way of circumvent the problem, which is doing better feature engineering. If you redefine your features, not to be x1 and x2, but a function of x1 and x2, like if you say that x1 prime is the end of negated x1 and x2, and x2 prime is the end of x1 and negated x2, then these circles in this new representation are going to collapse, and now we can find a separating hyperplane. But for doing that, we had to do this feature engineering. Okay. So tomorrow we're going to learn that instead of doing this feature engineering, you can also use a multi-layer perceptron. And the multi-layer perceptron is going to learn an internal representation that allows us to do this separation. But this is something that a single perceptron cannot do in the original feature space. So this result is sometimes attributed to Minsky and Papert, but this was known well before, in the 40s. There is a very famous book by Minsky and Papert from '69, which is associated with the beginning of the AI winter, the first AI winter, that shows a lot of limitations of multi-layer perceptrons, but it was not exactly this XOR problem. And Biksha, I think, is going to talk a little bit about this tomorrow. Okay, so let's see. Oh, I think I'm very late. Okay, I think I will speed up, but before doing that, any questions? Okay, so now let's assume a multi-class classification problem that can have more than two labels. One strategy for multi-class classification is just to train one binary classifier for each label. If you have a binary classifier for each label, then we can just use a technique called one versus all, which is picking the class with the largest score. and use it as our prediction. There is also other strategies that involve voting. For example, 1 versus 1. If you make if you train a binary classifier to distinguish from each label to every other label, and then you do voting, then you can check which of the labels has the most votes. But here in this class, we are going to consider classifiers that are actually tackling these multiple classes directly by designing a suitable loss functions for them. So if you want to go multi-class, there's a few steps that we need to do. Now we need to have not a weight vector, but a weight matrix. I'm going to use uppercase notation for matrices. So W is now a matrix which is number of labels times number of features. So there is one row corresponding to each label, to each class. Another way of thinking it is that each entry of this matrix, each weight, corresponds to a pair of a feature and a label. And we also have a bias vector, not just a bias coefficient. So we have a bias coefficient for every class. Okay. So another way of thinking about this is that we have a number of weight vectors which corresponds to each label. So we have several weight vectors wy. I'm indexing here the label for that corresponding weight vector. Each of these weight vectors is a row in this matrix, and we have scalars by. Okay, and then again, what we are going to do is to obtain a score for a particular label by applying a linear combination of features and their weights. Okay, so this part is similar to what we were doing before. But now we are using the label specific weight vector. Okay, so for every label y, any candidate label y, we take the corresponding weight vector wy, which is a row of this matrix. We multiply it by the feature vector phi of x. We add the bias coefficient by, and this is going to give us a score. And we're going to do that for every candidate label, and then you pick the label that has the highest score. Okay, so this corresponds to this argmax operation. We are going to pick the label y hat that maximizes this score. Okay. Okay, so geometrically, these classifiers are going to split the feature space into regions which are going to be delimited by hyperplanes. So you have something a little bit more like this instead of the single hyperplane as we had in the binary case. And there's also, you can also think of these in terms of a neural network. If you have more than, well, in this case, it's two labels, but if you have more than two outputs in your neural network, then it's common to use this notation where we just multiply using matrix notation. We multiply our weight matrix W by the feature vector phi of x. This is going to result in a vector, which is going to be the dimensionality number of labels. We sum the bias vector, and then we pick the index of this vector that has the maximal value. Okay, this is the argmax of the vector, and the result is going to be the index that corresponds to our predicted label. Okay. All right. So one thing that is important to take into account is that this formulation using this argmax recovers the binary classifier as a particular case. Okay, so if you only have two labels, +1 and -1, if you apply this rule, we are going to, we're going to look for the maximal score, the label among these two that has the maximal score, and so of course we only need to compare two things. When we use W equals to +1, if this score is bigger than the corresponding score when y is -1, then the prediction is going to be +1. Otherwise, it's going to be -1. And now having this part bigger than this part is the same thing as having this minus this greater than 0. Okay, so another way of expressing this is the sine function of the difference between the weight vector corresponding to the positive class minus the weight vector corresponding to the negative class. I'm just calling W this difference times phi of x plus the difference between the bias vectors b +1 and b -1. Okay, and I'm just going to call b this part. And this is exactly the expression that we had before for the binary classifier. Okay, So this is showing that these two things are equivalent. We still recover the binary classifier that we had today, but we are now using double of the parameters that we need. Okay, so for the binary classifier, using the notation that we're using before, we just need W. We don't need W plus 1 and W minus 1. We just need half of the parameters, and the same thing for the bias. We just need a single bias, not two. Okay. Any questions? Okay, so all right. So our prediction rule is going to be this. So we compute the score using every candidate label Y, and then we predict Y hats that maximizes this score. And again, in the binary case, this is going to revert to a simple hyperplane classifier. Okay. All right. So again, it's common to omit the bias vector B. We don't really need it if we assume that there is a constant feature. Okay. So if there is a constant feature, then the first row, the first column, the first column of the weight matrix is going to correspond to the bias coefficients. Okay, so we don't really need to explicitly use the bias vector, and from now on we are not going to use it just for simplicity. There's also a version of the perceptron that works for the multi-class case. It has a very similar mistake bound, the same guarantees. If the data is separable, it's guaranteed to find a separating hyperplane. It's essentially the same thing. The difference is that now we are making this prediction using this argmax rule. And then instead of one update, you need to do two updates. This just means that we have our weight matrix double, and you need to update two rows of the matrix. For the row that corresponds to the correct label, we need to sum phi of xi. For the row of the matrix that is indexed by the prediction of the model, which is wrong, we need to subtract phi of xi. Okay. If you do this, then we have the same guarantees as the binary perceptron. Okay. Okay, so now I'm going to move to naive Bayes, and then we're going to do the break. Or maybe you can do the break now, and do you do naive Bayes afterwards? Yeah. Okay, let's do that. So let's do the break and then do naive Bayes. All right. Okay. So let's get started with the second part. In the first part, we talked about regression, then classification, we covered the perceptron. Now we are going to talk about the naive Bayes. So there's lots of materials for the second part, but I think I might skip some parts to give time. Okay, so now let's go back to probabilistic models. If you remember this initial example that I was showing with the sequences, the description was not talking about linear classifiers or anything like that. Okay, so we are just talking about probabilities and how to estimate probabilities. So let's assume that our goal is to model the conditional probability of output labels y given inputs x. So we want to model p of y given x. If you are able to estimate this distribution, then we can predict our labels by picking the y that maximizes this probability for a given x. And one way to model this conditional probability is to apply Bayes' rule. If you have a prior probability for the labels p of y, and you have conditional probabilities p of x given y, so how to generate data conditioned to labels, then you can apply Bayes' rule. And if you want to pick the y that maximizes this conditional probability, we don't really need this denominator because this p of x does not depend on y. Okay, so maximizing p of y given x is the same thing as just maximizing the numerator with respect to y, which is going to involve these two terms. Okay, a prior probability on the labels and conditional probability, probability of x given y. Okay, so and these two terms, together they are basically the joint probability of x and y. So it's common to look at to these methods and come up with a generative story for our data. You can assume that there is some mechanism that generates the data that first picks a label according to the distribution P of y, and then when the label is picked, generates our examples by using the distribution P of x given y. So you're kind of reverting the process of estimating the label given the data by assuming that nature first generates a label and then from that label generates something. And this is called, models that consider this joint probability that work this way, they are called generative models because they come with this generative story. So this is something that you'll see more details later in Noah Smith's talk. But the method that I'm going to talk about now, naive Bayes, is an instance of a generative model. So let's come up with a concrete example. Let's assume that our input x is partitioned as a composition of other variables, other random variables, v1 to vl, where each of these variables belongs to some domain. Okay, so for example, we can assume that x is a document. For now, let's assume that the length of this document is fixed. So all documents have the same length. This is not very realistic, but it's just convenient for this explanation. And we can assume that vk corresponds to particular words of that document, the word at position k. We can also assume that there is a fixed vocabulary for all positions. So all words are picked from the same vocabulary that we are going to call V. Okay. So the naive Bayes assumption, the assumption that this model is going to make is that we are going to assume that all the words, all the V's are conditionally independent from each other given the label. Okay. Which is different from them being conditionally independent. So only when they are conditioned on the label, they are independent. Okay. This is very important. This is the same thing as saying that the conditional probability of V1 to VL, which forms our document X given Y, equals the product of the individual probabilities of each VK given Y. Okay, so if you do that, then the joint probability of X and Y can be written as the product of the prior probability on the labels plus this product that comes from the naive Bayes assumption. Okay. And note also that this assumption assumes that the word order is not important. Okay, so if you have the document with the same words but in different orders, if we are scrambling the words, then because we are just using the product of the probabilities, this is going to result exactly in the same distribution. So this is implicitly making this back and forth assumption. So there is a small caveat in this model, so which is that documents have a fixed length L. I mentioned this before. This in practice is not realistic. It's actually possible to deal with variable length if we introduce also distribution over the document length. Okay, and we can choose whatever distribution we want. So in this case, you want to have a probability mass function that works with discrete data because length is a discrete quantity. So a good choice would be, for example, a Poisson distribution, where you could fit this Poisson to data, and parameterize this distribution, by fitting this model to the data, and then the joint distribution of x and y will be written as not just the product, the prior P of y, and the product that we have seen before, but we also need to take into account the probability of this particular length. Okay. In practice, this is not going to matter because this probability of the length of the document is going to be independent of y. Okay. So if you just care about the y that maximizes the probability, we don't need to use. You can ignore this term safely. So nothing is not changing. Nothing is really changing, and you get exactly the same posterior as before. Okay. So let's just ignore the length. And let's think again about why did we come up with this assumption. So one benefit is that this is going to reduce considerably the number of parameters. So for example, if you haven't done any factorization assumption, so if we didn't use this naive Bayes assumption, if you were going to model this probability distribution directly, how many parameters will be required for expressing this distribution? Assuming that we have a vocabulary V and we have documents with L words, how many parameters will be necessary? Anyone? More than that, because we are modeling the joint distribution of all the words in each of these positions, right? Worse than that. Anyone? It's going to be exponential in the length, right? Because you need to consider, all combinations of words for every position. So it's V times V times V, L times. So it's V raised to L, okay? This does not scale if L is large. And not only it doesn't scale, it's also going to, because many of these, unless you have a lot of data, we are likely going to have many sparse observations, right? So there's many combinations of words that you never saw. And this is going to give us unreliable estimates of these probability values. So we are going to have a lot of statistical noise by doing that. And on the other hand, if we do this factorization assumption with naive Bayes, how many parameters do we have? No, because we are estimating. So the only thing that we need to estimate is the probability for each word in the vocabulary given a label. Okay. So the answer is just linear in the vocabulary size. Okay, so it's basically the number of labels times the number of words. I'm ignoring the number of labels here because I'm assuming that the number of labels is a lot smaller than the vocabulary size. But you can see that by doing this assumption, we reduced from something that was exponential in L to something that is independent from L. Right? The complexity is just the same as the number of vocabulary terms. We just need to estimate one probability for every word in the vocabulary. Actually, as many probabilities as number of classes, but it's a huge reduction. So this is one of the big motivations to do the naive Bayes assumption. It might be too strong of an assumption because words are not really independent. The order of words is important, but for many tasks, it still works quite reasonably, and it avoids having to estimate too many values. Of course, if you have less parameters, then we also have less computation. There's less risk of overfitting. But we still have some risk of underfitting. Okay, so because our independence assumptions might be too strong. Okay, so let's see how we can learn, how we can estimate these parameters in the naive Bayes model. So this is the expression for our joint probability of X and Y. We assume, as before, that we have a data set with labels because we are working in a supervised learning scenario, and we assume that all the examples are IID. The parameters that we need to estimate are these sets of probability distributions. You need to estimate the prior probability of the labels, P of Y, and we also need to estimate for every word in the vocabulary and for every label the probability of V given Y. Okay. All right. So the classical objective to optimize for in a model like this is maximum likelihood estimation. This is the most common criteria, which means that you need to choose the parameters that are going to maximize the likelihoods of the observed data, the training data. And the likelihood is just the product, because we are assuming that examples are IID. It can be written as the product of the joint probabilities xt, yt for every input-output pair in the training data. And because we chose to represent our probability distribution this way, this can be written as a product of the probability of the label and times the product of the probability of each word for that document given the label. So we end up with this expression. And it turns out that for the multinomial naive Bayes model, the model that I had described in the previous slides, the maximum likelihood estimate as a closed form solution. And it all boils down to counting and normalizing. So it's exactly as we did for that example with the sequence. And I'm not going to show the proof here, not this time, but actually I think that in this lab, you might, I don't remember if you still need to solve the exercise or not, but it's somewhere mentioned in the lab guide how that works. So skipping a lot of details, the way to do that is, again, maximizing these is the same thing as maximizing the log of these. Then logs of products become sums of logs, and then by analytically maximizing that expression, you end up with this solution, which is the maximum likelihood estimate for these probabilities, okay, which is very intuitive. So the estimate for the probability of the labels requires just counting how many times for our n examples, how many of them have the label y, okay? So this means counting. This notation here is called the Everson notation. It's one if the property, if what's inside the brackets is true, otherwise it's 0. So this is just counting for every example if the label is y, which is the same thing as counting how many y's we see in the data, and dividing by the number of examples. So this is the relative frequency of the label in the data, okay? And this is going to be our estimate of the prior probability of the label. So yeah, exactly what we would expect. And the second term is basically counting how often we saw this word v together with the label y in the data, divided by how many words we saw for examples that have the label y. So this is an estimate for the probability of v given y, okay? And as we have estimated this thing for all labels and this thing for all labels and all words, then we have all the ingredients that we need to apply the naive-Bayes model to concrete examples, okay? So let's look at a concrete example for a sentiment analysis problem. Again, with a very small data set to make it easier. So let's assume that we have a corpus of movie reviews with very short reviews. Only 7 examples, where 3 of the examples have a positive sentiment and 4 of the examples have a negative sentiment. And let's assume that we are going to use just the adjectives as features, okay? So we have some part of speech tagger that identifies which of these words are adjectives, and those words are going to be the features for our model. So the first example is going to be represented by the words great, excellent, renowned, and the class is positive, and so on and so forth for the other examples. So if you use this model, we can start by estimating the prior probabilities for the labels, okay? And this is very easy. We have 3 positives out of 7 and 4 negatives out of 7. So the probabilities are just going to be 3 divided by 7 for the positive class and 4 divided by 7 for the negative class, okay? Okay, so this part is easy. Then we also need to estimate the probability of each word given a class, which means that you need to count how often we saw each of these adjectives together with a particular class, divided by how many adjectives we saw in total for that class. So for example, if you want to estimate the probability of amazing given positive, we are going to see 2 occurrences of amazing in examples that have the positive label, and they're going to see 10 different occurrences of adjectives in the positive label, okay? So basically, we have amazing here. This is a positive example, and amazing here also with positive. And if you count how many blues we have here in these first 3 examples, which are all positives, it's going to be 10. Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so these 3 exclamation marks also count as a feature. Okay, so we can do the same thing for all the other words and the 2 classes, and this is going to give us estimates of these probabilities. And now that we have all these estimates, then if we have a new document that we never saw before, so this is a new review. The text is, this was a fantastic story, good, lovely. There's 3 adjectives here, fantastic, good, and lovely. Then we can just use our estimates to compute what is the most probable class. Okay, so we need to compute this quantity here, which involves multiplying the prior. So let's start with trying y being positive, and then we need to try also y being negative. When y is positive, we need to have the probability of positive, which is 3 divided by 7. times the probability of fantastic even positive. You know, we can look here, fantastic even positive. It's 1 divided by 10. And it is good given positive 1 divided by 10 and so on. And you get this probability. And you need to do the same thing for negative. We never saw the word fantastic with negative. So this ends up having a probability of 0. And as a result, because we are multiplying all these probabilities together, we end up with an estimate of 0. So comparing these two numbers, it's more likely that the class is positive. So our predicted sentiment is going to be positive, okay? Which seems quite reasonable for this review. Here's another example. So here we have great plot, great cast, great everything. And by using the same strategy, the probability of positive is 3 divided by 7. Probability of great given positive is 1 divided by 10. Well, and so on. So now we have 3 occurrences of great. So we need to multiply these values 3 times. If you do the same thing with negative, it turns out that the word great occurs twice in negative examples. So it's actually more likely to have great in negative reviews than great in positive reviews, maybe because of the sparsity of our data. You know, we have lots of reviews that says that the movie is bad, but the cast is great. And here, great movie, but so, you know, sometimes adjectives that have a positive polarity can also be used in negative reviews. And as a result, our model is going to end up predicting negative because this second probability is higher. Okay. Any questions about this? Okay. Okay, so let's look at the last example. Now we have boring movie, annoying plots, an imaginative ending. If you use the same strategy, we can count how often we saw boring together with positive, it was 0, annoying together with positive, it was 0, and imaginative together with positive, it was 0. If you do the same with negative, you get 0, 0, 1. But in both cases, we have a probability of 0. Okay, so what should we do in this case? Right? So you get 0 probability both for the positive class and the negative class. Okay, so it's not clear what you should do. We have a tie, but this is a bit strange because this is telling us that the data that you are observing is impossible. It has a probability of 0. So there should be something wrong with the way we are estimating these probabilities. And this is actually something very frequent that has to do with the sparsity of our data. We have a very large vocabulary. We didn't observe enough examples to have seen exactly at least one instance of that word together with the review of each class, which is going to result in probabilities of 0 to many events. And because we are multiplying probabilities in the naive Bayes model, it only takes one word to have a 0 probability to zero out the entire probability, the joint probability of X and Y. Okay, and this can be bad, right? So the solution to this problem is to do some kind of regularization. Okay, and the most simple kind of regularization that is made in the naive Bayes model is something that goes by several names. People call it Laplace smoothing, Edwin smoothing, and so on. But the intuitive idea is very simple. It just assumes that every word has a pseudo count of 1 in addition to the true count. So it's like you had a pseudo document that contains every word together with each label. And in order to estimate our probability, we don't only count how many times things occur together and normalize. We add 1 to that. And then when normalizing, we need to add the vocabulary size so that the probability still sum to 1. Okay. And if you do that, then we never are going to get 0 probabilities because we are adding this positive quantity here. Okay. So we are not going to have the problem that I showed in the previous slide. Does this make sense? Okay. Have you seen this before? Okay. How many of you already knew the naive Bayes algorithm? Naive Bayes model. Okay. All right. So now if you take the same example that we had before, we get a probability of, this value. It's still a very small number, but it's not 0. We get this number for the positive class and we get this for the negative class, which makes the model predict negative. Okay, so one interesting thing is that, when I first started by talking about linear classifiers, the perceptron and so on, then I switch to naive Bayes. It turns out that the multinomial naive Bayes, so naive Bayes together with this multinomial distribution that I showed as an example for text classification, is actually an instance of a linear classifier. I think you are going to see this in the labs as well. But to show how, if you let the log of the prior, if you call it by, okay, for every class, for every label y, and if you let the log probability of a word v given the label be a weight that we are going to call it wyv. So it's a weight that depends on the label and the words. And you define features, which are just counts, how often a word v occurs in document X. Then it turns out that the y that maximizes this probability, which is the same thing, given our naive Bayes assumption that the probability of this, if we take logs, log is a monotonic function, so we can do that without changing the argmax. This becomes argmax of log of p of y plus the sum of the log of p of vk given y. And then by using the variables that we introduced here, we can write everything as a bias term, by, plus a dot product between a feature vector phi of x and the weight vector wy. And this is exactly the expression that we have for linear models, okay? So this means that the naive Bayes is a linear model in disguise. Naive Bayes with the multinomial model. It's an instance of a linear classifier, okay, for a particular kind of features, and where the weights and biases are related to the probability estimates. Okay, so let's recap a little bit what we have done. So the naive Bayes model, as I was pointing out in the beginning, is an instance of a generative model. This kind of models attempt to model inputs and outputs. It models it's estimated by doing maximum likelihood estimate of the joint distribution of x and y. And one benefit of generative models is that we can do more things with them rather than just predicting labels. For example, we can also sample documents from a multinomial naive Bayes model. How can we do that? It's very simple. We first sample a label according to p of y, because we have an expression for that probability distribution. And then we sample each word one at a time, conditioned on that label. And the result is going to be a bag of words. Okay, so it's not going to be a great document, not very fluent, because we are discarding word order and all that. But it's going to be a sample according to our distribution for data points. And all generative models, because they have a generative story, they allow us to generate data. But one thing that you might think of is why, if all that we want to do is to predict the label of a given document, we don't really need to generate documents, right? So maybe we are trying to estimate something harder than what we need to do. We don't really need to model the inputs. So an alternative strategy is to use discriminative models instead, where we don't care about the joint distribution of x and y. We only care about the conditional probability of y given x, because we always observe x. So why don't we estimate directly the probability of y given x? And this is what leads to what I'm going to describe next, which is logistic regression, which applies maximum likelihood estimation directly to the conditional probability of y given x. Okay, if you think about perceptrons and SVMs we haven't covered yet, and we probably won't have time to cover. But if you think about perceptrons, they are not a probabilistic model, but in a way they are also discriminative models. They don't care about the joint distribution of input and outputs. They assume that the input is given, and they just want a model that produces a good estimate of the output. Okay, so there's lots of choices for generative and discriminative models. We are going to revisit this question later in Noah Smith's class. They essentially differ in what distribution they use to fit the model parameters to the data. There was supposed to be a coffee break here that you already did. So, okay, so far we have covered the perceptron, naive Bayes, now we are going to move on to logistic regression. So just a reminder, this is the scenario that we are considering today. We are focusing on what we can see, if you prefer to think about neural networks. We are focusing on the output layer of neural networks, where we just have a bunch of features, which might be internal representations or handcrafted features. And we want to predict labels based on those features by using a linear classifier. And the linear classifier, assuming that we are working with multiple classes, more than 2 in general, we can write it as by picking the index that refers to the label that maximizes the product of the weight matrix W and the feature vector phi of X plus the bias vector B. Okay, where this matrix W has 1 row for every label, and each of these rows corresponds to a label-specific weight vector. Okay, and the bias vector B has 1 bias coefficient for every label. Okay, so how can we map a set of labels? If you want to have a probabilistic model, if you want to compute the probability of a label, a key problem is the thing that we are computing here. W phi X plus B. This can be interpreted as a score for every label. Okay, so if you have 6 labels, this is going to give us 6 scores. But if you want to have probabilities for each label, a key problem is how can we map this set of label scores to a probability distribution? Okay, if you want to compute a probability for every label. The most common way to do that is softmax. This is what I'm going to present next. There are alternative ways, including something called sparse-max, but I don't think I will have time to get into details about sparse-max. But yeah, let's start with softmax, which is the operation that is used in multinomial logistic regression. So in logistic regression, what we have is essentially a linear model that is going to give us a score for every class. This is the same that we had for the multi-class perceptron that we talked about before the break. And the thing that is going to change is that now we are going to convert these scores into probabilities by doing something called the softmax transformation. Okay, this means the following: we are taking each score. So this part here can be interpreted as a score for class Y. We are going to exponentiate it, and by exponentiating, we are going to obtain a positive number as a result. And then we are normalizing. Okay, and the normalizer is just the sum of all exps of all the scores, okay, where the sum is over all the labels. So by construction, this is the numerator is always positive because you're applying the exponential transformation, and then the normalization ensures that things are going to sum to 1. Okay, so as a result, we are going to get a valid probability vector. Okay, a vector where all the probabilities sum to 1 and all the probabilities are positive. Okay, so if you define things this way, then now if you look at the Y that maximizes the probability of Y given X, taking the expression that we put here for this conditional probability, this is the same thing as maximizing this quantity. Now we can see that the denominator does not depend on Y, so we can just ignore it. We are maximizing the exp of this. And because the exponential function, just like the log function, is monotonic, maximizing the exponential of something is the same thing as maximizing just what's inside the exponential function. Okay, so this shows that if we define the probability this way, then the class that maximizes the probability is the same class that maximizes the score. Okay, this is exactly what we had before for linear models. Okay. Okay, so there is also binary logistic regression, which can be seen as a particular case of multi-class logistic regression. But sometimes you see it in a different form. Okay, so in this case, we have binary labels. We can assume they are +1 and -1. And we assume that the scores for the negative class are always 0. And the model only needs to parameterize the score for the positive class. Okay. If the score for the positive class is positive, then the positive class is more likely than the negative one. If the score for the positive class is negative, then the negative class is going to be more likely. And so then the probability of +1 given X can be written as exp of this score for the positive class divided by exp of 0, which is 1, plus exp of the score of the positive class. Okay, and this thing, which can also be written as it is here, is called the logistic transformation or the sigmoid transformation. Okay, it's something that you're going to see tomorrow in the neural networks class. It's a very common activation function used in neural networks. And it's a way of transforming a real number, positive or negative, into a number which is between 0 and 1 that you can interpret as a probability. Okay, and the point I want to make here is that this sigmoid can be seen as a particular case of softmax if you have only 2 classes and you assume that the score for the negative class is 0. Okay. Okay, so yeah, this is the shape of the sigmoid transformation. We are going to see more details about this tomorrow, so I'm going to skip it. And let's go back to the multinomial case. We're just analyzing the multinomial case, the multi-class case, because it's more general. So we have defined our probability distribution. We know how to, once we have the model, once we have W, you know how to estimate the most likely class, but we still have the problem of learning the model, right? So we still need to learn the weights. And we know how to do that in the perceptron algorithm, and you know what to do it in naive Bayes, and also in linear regression, where we have a closed form solution. So the most natural thing to do is to pick W that maximizes the conditional log likelihoods of the training data, meaning that we want our estimates W hat to be the one that maximizes the product of the probabilities of each example YT given XT. And now we can also take logs. And the log of the product is the sum of the logs. So we end up with this objective. And because of the parameterization that we chose for this conditional probability, we now have a log of this expression, which is a ratio of 2 things. And this, so the log of a ratio is the difference of the logs. So we get log of exp of this minus log of zx, and log and exp cancels. So at the end of the day, we get this part in red, which comes from the log of zx, and this part in blue, which comes from log of exp of this, where log and exp are going to cancel. Okay, so this means that the objective function that we need to minimize in logistic regression as these 2 different terms. Okay, so one term that uses the weights for the correct class, the ground truth class, YT, and something that acts as a normalizer that quantifies how much probability mass we are putting in all the other classes, including also the correct one. Okay, so, and we need to find W that maximizes or minimizes this objective. Okay, any questions? No? All right. Okay, so it turns out that this objective function is convex. I think Maru yesterday talked a little bit about what are convex sets and what are convex functions. And one very nice property of convex functions is that any local minimum is also a global minimum of the function. Okay, in particular, this means that it's not so important how we initialize. Regardless of how we initialize, if you are able to find a minimizer when things converge, then there is only all the minimizers that are going to find is also a global minimum. Okay, so there is no closed form solution for this minimization problem, unlike linear regression or naive Bayes. But there's lots of numerical techniques to optimize this problem. And this includes techniques like gradient methods, gradient descent, conjugate gradients, quasi-Newton methods like LBFGS, and so on. Today I'm going to talk about stochastic gradient descent. There is also, if you've ever heard of maximum entropy models, sometimes people use that name. They mean exactly the same thing as logistic regression. The reason why they call it maximum entropy is that there is a duality between maximizing conditional entropy with constraints and logistic regression. I'm not going to get into details, but this is the reason. Okay. All right. So let's recap that if you have a convex function, I think Mario talked about this yesterday, right? Okay. So if you have a convex function like this, you have the property that if you pick, 2 points in the graph of the function, then the straight line that connects the points is always, or the graph of the function is always below that straight line. Okay. If you want to find a minimizer of a function, you can also do this for functions that are non-convex. One popular set of methods are gradient descent methods, where we initialize according to some strategy. Let's say that x0 is our initial point. And then at each point, we are going to compute the gradients of the objective function with respect to x on that point. And we are going to make a small step in the direction of the negative gradient. Okay, so if this is the level curves of our function, then by following the negative gradient, we are going to move from x1 to x from x0 to x1. Then if you do another update on x1, we will move it to x2. And at each step, we are slowly getting closer and closer to the minimum, which is this point here. And the rule is very simple, right? So it's just this expression. Okay, you just need to be able to compute the gradient of the function with respect to xk. Okay. Okay, so let's get back to logistic regression and see how we can do this. So the loss function that corresponds to logistic regression is this expression here that I had in this slide. So we have the log sum x, which comes from this normalization function, and we have this blue part, which involves only the correct label, yt, and we need to be able to compute the gradient of that in order to apply the gradient descent algorithm. So you want to minimize, we want to find w that minimizes this loss function. We are going to initialize the weights to 0, all zeros, and then we are going to iterate until convergence. So at each step, we are going to compute the gradient at the current point w, and because this loss function, we need to sum overall data points. We need to compute the gradient. If you want to compute the gradient for the entire data set, this is the gradient of a sum, which is the same thing as the sum of the gradients. Okay. Okay, and because the loss function is convex, then we are guaranteed to reach the global optimum if you choose the step size accordingly. Okay, so in practice, this thing is a little bit slow because with the thing that I just described, which I just described, you need to compute the gradient for the entire data set. So you need to, before doing any updates on the weights, you need to touch every data point in your data set, compute the gradient with the corresponding W, and only after accumulating everything, you need to make a gradient step. In practice, what people do is a little bit different. If your data set is large, this is going to be too slow. And so it's common to do more frequent updates, okay? And one extreme case of that is stochastic gradient descent, where instead of computing the gradient of the entire objective, we do a very noisy estimate of the gradient, where we just randomly sample one example, and then you compute the gradient only with respect to that example. So instead of doing this sum here, we randomly sample xt, yt, and we just compute the gradient with respect to that data point. Okay, and by doing that, we do a lot more updates on W. Okay, in practice, this is going to converge a lot faster. There's also variants in between. Those are the most commonly used. They're called mini batches. What people do in practice is you don't update based on a single example, but you also don't do it for the entire data set. So we define some batch that contains some examples, and then you compute the gradient only with respect to that batch, and you do an update based on that batch. This is particularly convenient if you are, for example, training neural networks with GPUs, because you can parallelize the computation inside the same batch. Okay, I think you are going to hear about this in other classes. Okay, but the fundamental problem remains, okay? We need to be able to compute the gradient of the loss in logistic regression, which is the gradient of this expression. And I'm going to describe how you can do that. So there's a few properties of gradients that we need to use. I think that maybe you heard some of these in yesterday's class. One property is that the gradient of the log. So if you have a function f of w, the gradient of the log of the function equals 1 divided by f of w times the gradient of f. Okay, this is a generalization of the univariate derivative, where the gradient of log of x is 1 over x. Okay, or the gradient of a function is f prime x divided by f of x. Okay, so this is the generalization of that for functions that have that accept vectors as inputs, or matrices in this case. The second reminder is that if you want to compute the gradient of the exponential function, it can be written this way. So you have this formula. It equals the x of the function times the gradient of the function inside the exponential. Okay, so just by using these two properties, and also by using the special notation of a one-hot vector. Okay, so I'm going to use this notation EY. It denotes a one-hot vector, a vector that is 0 everywhere except in a single index, and that index is the one that is associated with a label y. So if you use this notation and those formulas, then we can compute, by following a sequence of steps, we can compute the gradient of the loss function of logistic regression and obtain a very simple expression in the end. Okay, so I'm going step by step because this part is relevant. So this is the loss function that we need to, whose gradient we need to compute. It has this part in red and this part in blue. Because we have the gradient of a difference of two terms, we can compute the gradient of the two terms and take the difference. So the gradient so we have the gradient of the red part minus the gradient of the blue part. Now in the red part we have a log, so we can just apply this formula here. Okay, so it's the gradient is going to be 1 divided by what's inside the log, which is this sum, times the gradient. The gradient of this, and because the gradient of the sum is the sum of the gradients, we can write it as the sum of gradient of x. And then in the blue part, we have the gradient of the dot product between the weight vector, which is a particular row of the matrix W, dot product between these and the feature vector phi of x, and the gradient of that is can be written as an outer product between a one-hot vector ui and phi of x. Okay, to get some intuition about why this is true, notice that for this single term, only the row of the matrix W that refers to label y is going to be relevant. So the gradient of all the others is going to be 0. And then when we take the outer products of ey with phi of x, this is going to put zeros in all the rows that do not refer to label y, and it's going to copy phi of x to the corresponding label. Okay. All right. So if you keep going, then we still need to work out this gradient here. We can also notice that the sum of the x is exactly what we called zx before. So this part here is just 1 divided by zx. And now this part here involves computing the gradients of this x here. And now we can use the formula for the gradient of x, which is x times the gradient of what's inside. If you do that, then we get x here times the gradient of what goes inside. And now we might see that you just put zx inside the sum again. And the gradient of this part, this is very similar to what we have in blue. But here we have y prime instead of y. But the gradient is going to be this, a one-hot vector with respect to y prime times phi of x transposed. And this part here, you might recognize it as exactly our definition of the probability of y given x. Okay, so it's exponentiating the scores and dividing by the normalizing factor zx. So this is exactly p of y prime given x times these things. And so putting everything together, and this is the only thing that you need to remember from all this exercise, is that the gradient of the loss function for logistic regression equals the difference between the probability vector according to our model W. Okay, so this thing is the probability vector. The dimensionality is the number of labels. Okay, the probability of each label minus a one hot vector that indicates the correct label. Okay, so this is a vector with all zeros except in the entry corresponding to the true label Y, where we have a 1. And then times phi of x transposed. Okay, so the result is going to be a matrix, which makes sense because the gradient with respect to a matrix W needs to have the same shape as this matrix. And yeah, so with these ingredients, we are now able to compute the gradient of the loss, which means that we can now use gradient descent to train a logistic regression model. Okay, so to summarize, what we did in logistic regression was we first defined a conditional probability according to this expression. Then we define as the criteria to maximize or to minimize a loss function, which is corresponding to maximizing the conditional log likelihoods of the training data. And then we computed the gradient of that loss. And if we run gradient descent, then we are able to converge to the global optimum of this problem. Okay. It's interesting to put everything in perspective now. So we first talked about naive Bayes. We saw that it's an instance of a generative model. It maximizes the joint likelihoods. We have a closed form solution for that just boils down to counting and normalizing. Logistic regression is discriminative, so it's not trying to build this generative story. It focuses directly on estimating probability of y given x. It doesn't maximize joint likelihoods, but rather conditional likelihoods, the probability of y given x, not the joint probability of x and y. It doesn't have a closed form solution, so it's a little bit more complicated than naive Bayes, but it's still a convex function to optimize. And if you do stochastic gradient updates, then the updates are going to take this form. Okay. And we also talked about the perceptron, which can also be seen as a discriminative, but a non-probabilistic classifier. And the updates in the perceptron, they take this form. Okay. This was there in the slide where we had the pseudocode for the multi-class perceptron. Okay. So basically it boils down to when you do a mistake, you need to subtract a row of the matrix corresponding to the wrong class that the model predicted. This corresponds to this term. And we need to add to the row that corresponds to the correct label the same feature vector phi of x. Okay. If you get the label right, if y is the same thing as y hat, these two terms cancel. So it means that you are not updating anything. Okay. But this is a way of expressing the updates in perception. Now, if you look at the updates in stochastic gradient descent for logistic regression and the updates for multi-class perceptron, they're actually quite similar. So if you look at this part in blue, it's exactly the same. Okay. The part in red, it's a bit different. In one case, in the perceptron case, this part in red is just the corresponding row of the matrix that corresponds to the wrong prediction of the model. In the case of logistic regression, it's like a soft version of that, because we are using the probability that the model assigns to each label, and then we are multiplying that. By the feature vector phi of x. So we can regard the updates in logistic regression as kind of a soft version of the updates in perception. But it's interesting to notice that they look similar. Any questions at this point? Okay. All right. So I'm going to just briefly mention the key idea in SVMs, but I don't have time to get into details because I'm running late. So we talked about the separation margin when we prove the mistake bound of perceptron. You can define it. I think we did it for the binary classification case, but more generally, it corresponds to the difference between the score of the positive class and the score of the most competitive incorrect class. Using all the points that we have in our training data. And that difference is called gamma. And when we saw, so graphically, you can, if you have an hyperplane classifier like this, the margin corresponds to how far are the points from either of the classes to this classifier. Okay, so for example, here the margin, well, in this case, this is not, oh, sorry, this is testing. So in this case, the margin corresponds to the closest positive points and the closest negative, how far they are from the hyperplane. But if a set of points, if a data set is separable, we can see that there's multiple choices for where we place the hyperplane, where some choices will have a bigger margin than others. And when we talked about the perceptron algorithm, we saw that the perceptron is able to find the separating hyperplane, but it's not necessarily the one that has the largest margin. It's just the first one that the model finds. And we have a bound in the number of mistakes, but it might actually have a small margin. And there is some theory that I'm not going to talk about that states that if you optimize, if you pick the classifier that has the maximal margin, this is going to be the one that is going to give us the best generalization. So there is some theory that connects generalization error to unseen test data to the margin size in our training data. So SVMs, in one word, because I don't have time to get into all the details, you can regard SVMs as like something very similar to perceptrons, but where we try to find the classifier that has the largest margin. Okay, and this can be expressed as an optimization problem. And you can also optimize, it's a convex optimization problem. You can also use gradient-like methods, in this case using subgradients instead of gradients. And the result of that is, you do like a similar approach as logistic regression, and you have something that in the end is a little bit more robust than the perceptron algorithm. Okay, so I'm going to skip these slides and maybe just use the slides where we put everything in perspective. Okay, so this is basically a comparison of the updates that we do in the perceptron algorithm with the updates that we do if we use a subgradient algorithm to learn a Sopok vector machine. So the updates are very similar with some subtleties. So in the case of the perceptron, if the model does the correct prediction, we don't update. We keep it like this. In the SVM, if the model does the correct, if the model is correct, there are two things that can happen. Either it is correct and the margin is greater than 1. So which means that the score of the correct class minus the score of the most competitive wrong class, if this difference is greater than 1, then we also don't update. But if it's correct but with the small margin, then we still update. Okay, and then what is the other difference? Right, and then the other thing is that we consider not, the update is not with respect to the prediction of the model, but with respect to a cost augmented version that includes also a cost function between the wrong class and the correct one. So, okay, I'm going to skip details about SVMs. You can ask me later if you want more details. But so in general, we have seen these different linear classifiers: naive Bayes, logistic regression, perceptron, and SVMs. And now we are going to talk a little bit about regularization. We probably don't have time to get into Softmax, but I can present the main idea, and then briefly on nonlinear classifiers. So let's talk about regularization. We saw this before when we covered linear regression, that there is a trade-off that we need to choose between underfitting and overfitting. You don't want a model that underfits our data, like in this example on the left, but we also need to be careful because you also don't want a model that overfits the training data and then generalizes poorly to new data. We want to be somewhere in the middle. And one example of regularization that we saw, actually we saw two examples. When we talked about linear regression, you saw that we can use a Gaussian prior to the models that corresponds to using L2, an L2 norm regularizer. And then when we talked about naive Bayes, if you remember that example where a document had 0 probability to occur, because our probability estimates were too sparse, our data was too sparse, we saw that Edmonds smoothing or Laplace smoothing, which is the same thing, was a regularization strategy to improve naive Bayes. In general, there's other choices of regularization, but they all try to do the same thing. They try to penalize models that are too specific to the training data or too complex. And the reason how this is, the way this is formulated is by not just minimizing a loss function that expresses how well the model fits the data, but also include another term that depends only on the model and not on the data, that penalizes models that have high complexity according to some criteria. This is called, this omega of W is called the regularization function. And this lambda here is a coefficient that controls how much we want to regularize. Okay, so there is a trade-off. The higher the lambda, the more you regularize. But if you regularize too much, you might end up underfitting your data. Okay, on the other extreme, if you don't regularize enough, if lambda is 0, in that case, you're not regularizing, then you might be overfitting your data. So you need to tune this lambda as an hyperparameter in your model. And so the simplest kind of regularization is L2 regularization, which corresponds to using a Gaussian prior for the model. This is basically the example that I have shown when we talked about linear regression. And this means that we take our weights matrix W and we just sum all the squares of the weights. Okay, this is the L2 norm. So this means that if the magnitude of our weights is too large, this means that the model might be over-adjusting, trying to overfitting the training data. So if you penalize large magnitudes, and this regularizer does that, you might end up with a model that generalizes better. Another possible choice is using a L1 norm instead of L2 norm. I think Mario yesterday talked about different norms. Did he talk about the L1 norm? Sum of absolute values? No? Okay. He did? Okay. I think he probably did. So the difference between L1 and L2 is that in L1, we don't sum the squares, we sum the absolute values. Okay. And there is some connection between L1 and sparsity. I'm not going to talk about sparsity today, but it turns out that if you use L1 regularizer, then there is a propensity for your model to pick up a sparse solution, which means that many of the entries of the matrix W are going to end up being exactly 0. Okay, and if they are 0, this means that since we have weights multiplying by features, the corresponding features are going to become irrelevant, because 0 times the value of the feature is going to be 0. So this is a way of doing feature selection. Okay, we can throw away these features from the model. So L1 regularization was a very popular strategy for feature selection because of this property. And from a probabilistic sense, it's equivalent to using Laplace prior. So to use a prior for your weights that follows a Laplace distribution. Okay, so this states what I was saying before. There is this trade-off between model complexity and predictive error. Take this with a grain of salt. This is the classical statistical theory. With neural networks, this classical statistical theory is, it's challenged, and you have instances of double descent curves. I don't know if anyone is going to talk about that in the school, but it's a very active research topic. People are still trying to understand better what happens in that regime. But for the regime that I'm talking about yesterday with linear models, it's safe just to consider this scenario. Okay, so what is this? Okay, so if you take logistic regression, as we saw before, and we add L2 regularization, if we add this extra term here to regularize, and we use the L2 norm of the weights, and now we need to compute the gradient again. So the gradient is basically the gradient of the loss that we already obtained before, plus the gradient of the regularizer. And now, because the regularizer is just the L2 norm, the gradient is very easy. Okay, so the gradient of the L2 norm of W is just times lambda divided by 2 is just lambda times W. Okay, which means that if we plug that, okay, I'm not showing that. So if you plug that in the gradient updates in stochastic gradient descent, this is going to it's going to result in something called weight decay. So whenever you hear the expression weight decay, and this is a term that is widely used in the context of neural networks, this is equivalent to doing L2 regularization, to regularizing with the L2 norm. But so it's easy to plug this the gradient of this regularizer in our training. I didn't talk much about SVMs, but SVMs already have the L2 regularization built in. Right, this part is less relevant. So just a quick summary of loss functions. Loss functions should match as much as possible the metric that we want to optimize at test time. So someone asked in the morning about what happens if you have imbalanced data sets where one of the classes is much more frequent than other class. Then one way to try to compensate for that is to design a loss function that penalizes some kinds of errors more than others. And this is something that we should do. Not all problems are as nice as what I presented here. Sometimes you have to deal with the things that are not balanced, or sometimes some kinds of errors are much more dangerous than others, and we need to take that into account. So there's lots of things that go into defining loss functions. But there is also a trade-off because we want to optimize these loss functions. They need to be well behaved. They need to be continuous functions. It's good if they are smooth functions because you can compute gradients, even though SVMs, for example, they are not smooth. They're not differentiable, but they are continuous, and you can still compute not gradients, but subgradients, and do our optimization as normal. But you cannot easily optimize the 0-1 loss. The 0-1 loss is basically you get a loss of 0 if you get the correct label, and you get a loss of 1 if you have the incorrect label. This is discontinuous, and it's very hard to optimize a loss function like this. So some examples of loss functions that we saw today includes the squared loss for regression. We talked about negative log likelihoods or cross entropy. That is the loss function that underlies multinomial logistic regression. There is the hinge loss, which is the one that is associated with support vector machines, which corresponds to this idea of margin. And there is also another one called sparse max loss, which I don't have time to describe, but I will try to convey the main idea. And choosing the most suitable loss is very problem dependent. Okay, so just one quick thing about sparse max. This is actually work that came from our group. It's an alternative to softmax, where instead of exponentiating and normalizing, you do something a little bit different that is particularly relevant if you want to have a probability distribution that is sparse. So for example, if you are operating with a very large set of labels, and you believe that many of the labels are irrelevant, they should have 0 probability. Softmax is never going to give you 0 probability. It can be arbitrarily small, but it's never going to be 0 because the exponential function is strictly positive. Okay, so sparse max is an alternative transformation, which is defined as the probability vector that is the closest to the score vector in terms of Euclidean distance. That one has a propensity for sparsity. So it might be useful if you want to assign exactly 0 probability to a lot of labels. There's a lot of details here that I'm going to skip, but it's still computationally efficient to use it. You can use it both as a transformation, for example, if you're using a neural network, or as a loss function. And in 2 dimensions, it's interesting to contrast softmax, which corresponds to a sigmoid. This is the blue line here, and the one that you will get if you use sparse max, which is kind of a hard version of the sigmoid, which is a piecewise linear function like this. Okay, the same idea carries out also in 3 dimensions. Okay, so the softmax if you have 3 classes, softmax is this smooth surface here, and sparse max is something that has similar asymptotics, but it has this exact saturation, and it's a piecewise linear function again. You can also see sparse max, the transformation, as something which is in between softmax and argmax. So argmax is extremely sparse. Okay, it gives you a one hot vector as a result. It's just looking for the index that has the largest score. Softmax is not sparse. Okay, so it can give very small probabilities to some labels, but there's always going to be some positive value. So in this example, we have the same score vector, 5 labels. And this is what argmax would give, and this is what softmax will give. Sparse-max will give something in the middle. It will give a 0 probability to 3 of the labels, and a non-zero probability only to 2 of the labels. Okay, and it turns out that it's still possible to compute derivatives with respect to sparse-max and do optimization with it. If you're interested about sparse-max, let me know later. I don't have time to explain all the details here. Okay, so putting everything together, and I think this graph is like a summary of these different choices of loss functions. So this is for the binary classification problem. If you assume that the correct label is +1, and if you define the difference between the score of the correct label and the opposite. So the S is the difference of scores. So if S is positive, it means that the model is making a mistake. If S is negative, then the model is doing the right thing. So this is how the different loss functions compare with each other. So the thing in red, it's the 0-1 loss. Okay, this is the loss that sometimes you would like to use. It's basically you get a loss of 0 if you get the right decision. You get a loss of 1 if you got the wrong decision. It's like a sine function. Okay. The problem with that is that you cannot optimize that. There's many results that show that it's NP hard to optimize this loss directly. So the alternatives that are available are, for example, the perceptron, the loss that corresponds to the perceptron. This is the purple line here. It's 0 if the model predicts the right label, and then it increases linearly if the model made a mistake. SVMs is this light blue line. It's also piecewise linear. It's 0 if you have a margin bigger than 1, and then we start to pay a penalty, and this grows linearly. If you use a squared loss, it's also possible to use a squared loss for classification, even though it's not very natural. You also get penalized, even if you predict the right label, but if you have too large of a score. So logistic loss, it uses the probabilistic version, so it's this blue line here. And the sparse max loss, that was the one that was there in the previous slides, is something that is a little bit in between. It's on a smooth version of the perceptron loss, if you want. Okay, so how are we in time? So there's around 10 minutes. I think we are going to end on time now. So just another recap from today's class. We saw that linear classifiers can solve linearly separable problems, but they cannot solve problems like XOR that are not linearly separable unless we change the features, we change the inputs to be a better representation, right? In the XOR example, this corresponds to letting these 2 points collapsing as a single point, and then it's easy to separate them, okay? This is what corresponds to doing feature engineering, right? It means that, okay, this representation is not good. I need to define better features such that it's easy to find a linear classifier that separates the data. And we covered several things. All the things that we talked about today, they either have closed form solutions or they lead to convex optimization problems. So it's easy to optimize. There's no issues at all with local minima, with initialization, and so on. And we have always assumed, because this is assumed by these algorithms, that the starting point, the features that we start with, are already well engineered so that the data is either completely separable or at least nearly separable. But in practice, there's several things that might happen if the data is not linearly separable. So one strategy is just to engineer better features. This is the naive solution, but it's often a good one. Another possibility is to work on kernel methods. How many of you heard of kernel methods? Okay, more than what I expected. So kernel methods used to be very popular, 10, 15 years ago. It's a beautiful theory. It basically states everything in terms of similarities between data points. And it's possible to show that many of all the algorithms that we cover today, there is a counterpart that do not use explicit features. It only involves computing a kernel function between data points. And implicitly, there is well, I'm going to cover them. They will work implicitly in a high-dimensional feature space. They don't completely solve the problem of engineering because you still need to choose or to design a good kernel function, and that might also be hard. And they are not as flexible as neural networks. They still result in a convex optimization problem, but we are also limited by having to use something called positive definite kernels. The next class tomorrow, Bixo is going to talk about neural networks, where we just stop trying to get something convex. You just embrace non-convexity and local minima. And instead of spending energy engineering features or kernels, you just spend effort designing a good model architecture, and you get for free good internal representations that avoid having to design explicit features. Okay, but so I want to finish by building a little bit on this perspective, these two different perspectives of building machine learning systems. The one that we focused today was essentially feature-based models, where the goal is to design features that describe properties of objects or inputs. For example, what are the words that are occurring in a document? What are something that occurs in an image, and so on. And then you build models that manipulate these objects' properties. But there is another class of methods which works in a bit of a different way. They don't try to describe objects, rather properties. Instead, they have a notion of similarity between objects. So they do things like, okay, this input is very similar to this other input. Maybe I should take inspiration on the labels of these inputs to predict the label of this other one. And this is something that underlies methods like the k-nearest neighbors, many of the kernel methods, things like Gaussian processes, and so on. And interestingly, sometimes these two perspectives are dual of each other. They might be equivalent. So let's start with the nearest neighbor classifier. How many of you have heard about the nearest neighbor classifier before? Okay, it's almost everyone. So the nearest neighbor classifier is not, in general, a linear classifier, but it's a very, very simple classifier. It works as follows. You memorize all the training data. Usually it boils down to having efficient data structures that are able to represent your training data efficiently if you have a lot of data. And then if you are given a new input X, it works by finding the most similar data point according to some metric. And it's a very active area of research trying to come up with a good metric to embed our inputs. So it finds the most similar data point, and then it predicts the label of that data point. It's a very intuitive idea. There are many variants of that. For example, instead of using just one neighbor, you might look at k neighbors, and then having a way to combine these k neighbors. For example, using their distances, their similarities, and interpolating with that. There is a disadvantage, which is if you do it naively, every time we have to classify a new input, we need to compare with all the existing data points that consist in our training data. And this might be an expensive operation. But as I was saying, there are specialized data structures that can make that easier. And I would say that there is a little bit of a comeback of neural neighbors classifiers and many ways of combining them with neural networks. So there are several models that combine retrieval with generation, for example, where they use retrieval to find neighbors, and then they have a way of combining those neighbors with something that is some representation that is produced by a neural network. And these things are becoming very popular. Okay, so this is nearest neighbors. Now, kernels bear some similarity with nearest neighbors in the sense that they also rely on this notion of similarity functions. So they have this notion of kernel functions, which is a way of expressing a similarity between two points. Okay, so if you have two examples, xi and xj, k of xi, xj is basically a number that expresses how similar these two examples are. And if you have a data set with n examples, then you can form a matrix that contains all the pairwise similarities between all your examples. And forget for a moment that n can be very large. in which case it's not feasible to store these metrics in its full form. And so there is a bunch of properties that are necessary to make a kernel be positive semi-definite, which is like a key property in kernel methods. One is that the similarity between I and j, xi and xj, is the same as the similarity between xj and xi. So if you flip the arguments, you get the same value. This means that it's symmetric. The second property is being positive definite, meaning that for any data set that we can form, by forming this matrix K, this is called the Gram matrix. For any choice of vector V, then V, actually this should be V transpose KV and not VK V transpose. So V transpose K times V is greater than or equal to 0. And if we have a kernel that is symmetric and positive semi-definite, there is a classical result that comes from several people, including Mercer, but also related to something called reproducing kernel Hilbert spaces, that says that the kernel is equivalent, it equals to inner product in some feature mapping, in some feature space. So there is some function phi which defines how do you express our objects in terms of feature vectors, such that this kernel function equals the dot product between feature vectors of the corresponding points. And this theorem is very powerful because it says that for every algorithm that operates with features, or for many of these algorithms, there is a counterpart that uses kernels where we never need to operate directly on the feature space. This feature space can be very high dimensional. It can be even infinite dimensional. It can be a space of functions, but we never need to compute explicitly in the space of features. We can do all the computation just by evaluating kernels. And so originally the SVMs were used together with the kernel trick. So it was common to use SVMs with a kernel function, but we can also use SVMs with features. And the version that, well, I didn't actually talk much about SVMs, but the version that I have in the slides is basically just with features without kernels. But all the other algorithms that I talked about today, Perceptron, Logistic Regression, for all those, we can apply the same kernel trick and have versions of these algorithms that use kernels and not features. So, this was an extremely popular idea in the 1990s and 2000s. But it doesn't scale very well if you have a very large data set, because it requires these pairwise comparisons with different data points. There are ways of approximating it, but ultimately there was in the last years people abandoned a little bit the kernel methods in classification problems. Okay, so kernels are a way of having some tractable nonlinearity by defining these kernel functions and these implicit feature mappings. You are able to get classifiers that in the original feature space, in the original input space, sorry, are not linear. They are going to become linear in some abstract feature space that we never need to compute there. But it's useful if, for many problems. For example, if you have a data set that looks like this, like a bunch of points in one class, a bunch of them in the center, and then several of them around it. This is something that you cannot solve with a linear classifier directly, right? But if you define a kernel function, a suitable kernel function, in this case, a polynomial kernel, then this is going to implicitly correspond to a higher dimensional feature space with one extra dimension, where it's very easy to find a separating hyperplane. Okay, so kernel methods enable this. Okay, so there's many choices of kernel functions: polynomial kernels, Gaussian kernels. They're also called radial basis kernel functions. There's also kernels for discrete data, including kernels between strings, between sequences, tree kernels. And sometimes you still see these things being used in several applications, but they are not as popular now than what they used to be. Okay, so I think this should be it. So there is a notion that might be useful for the labs today, which is that of joint feature mappings. I'm just going to mention it very briefly because in previous years, several students were a bit confused by that when they saw that in the labs. So in everything that I presented here in the slides, when I talked about features, it was only phi of x, features that depend on the input only. They don't depend on the label. But it's also possible to define something called a joint feature map, which are features that depend on the inputs, but also on the label. And if you deal with these joint feature maps, then the notation changes a little bit. So you can express, you can have a weight for the different features, and deal just with weight vectors as opposed to these weight metrics. So here's an example. For example, if X is a document and Y is a label, we could define a feature. I'm using the letter psi for these joint feature mappings. We could define a feature that has the value 1 if the document contains the word interests and the topic of the document, the label, is financial, and 0 otherwise. Or I could define a feature which is the percentage of words in X that are punctuation, and the label could be the word scientific, and several other examples. So all these features are combining properties of X with properties of Y. And right, so this is yet more examples. If you want to classify entities in a document, you can also compose things this way. Okay, so the crucial thing that I wanted to point out here is that in this talk I used this notation phi of x, which does not use the output anywhere, and the equivalent thing, if you want to use joint feature mappings, is to do the cross product between these feature vectors and a one-hot vector that indicates the label. So this is basically stating that the feature vector for a given x and y is going to be 0 for all the entries that do not correspond to the label y, and then we are just copying the vector phi of x to the slot that corresponds to the right label. So we can regard this, if you unflat this vector, then this is going to be a matrix which is going to be the same shape as the weight matrix that I was talking about before. This is just a small detail, but you might want to come back to these slides later in the labs if you are confused with these things. Okay, so this is basically it. I think I'm going to jump to the conclusions. So we talked about linear classifiers. They are a broad class. They include well-known machine learning methods like the Perceptron algorithm, models like naive Bayes, logistic regression, support vector machines. They all involve manipulating weights and features. They either lead to a closed form solution or to convex optimization problems where you don't have any local minima. Stochastic or anti-descent algorithms can be very useful, in particular when training data sets are large. And this is a property that we also use in neural networks. However, these linear models have the disadvantage that they need to require manual specification of the feature representation. This is what is called feature engineering, which can be very tedious. And tomorrow in the neural networks class, we are going to, so Bixby is going to cover methods that are able to learn internal representations. So this is it for today. So if you have any questions, I'd be happy to take those. If not, I'll see you in the afternoon. No questions? Okay, so enjoy lunch. And in the labs, we're going to play a little bit with exercises around these topics. And then in the afternoon, you should come for Slav Petrov's talk, which is not related to linear classifiers, and it will be like an appetizer for what's going to come after this. Thank you.